US Department of Energy managing the flagship theoretical condensed matter physics program from 2008 to 2010. He is an academic editor of International Journal of Physics and Chemistry of Solids since 1994. The funding director of NU's Advanced Scientific Computation Center since 1999 and served as a various international editorial boards and commissions. He had authored and co-authored over about 400 technical articles and 18 volumes of conference proceeding, covering a wide range of the topics in theoretical condensed matter and material science, and a major books on X-ray Compton scattering from Oxford University Press. Bansal is highly cited researchers in ISI Web of Science and Clarivet analysis in 2017 and 18. I welcome to Dr. Bansal to present the work to our participant. Over to Professor Bansal.
Giving this presentation. It's amazing that one can sit in Boston and make this presentation. So what I thought I will do is share with you some recent surprises in topological and non-topological materials. Now, you may not find some of this surprising, but at least I find it surprising. So I will say a few words, perhaps more, before speaking about a large body of research on topological materials discovery. Of course, I can't cover everything, but I think a few highlights. There are many interesting light matter interactions that we are finding, and I will share a few of those with you, and then say a few words about cuprates, heterostructures, and battery materials. So with that, let me first thank my many collaborators that I have been very fortunate to have. And here I'm listing some of our theory collaborators, recent people we are really working with even now closely. Now, of course, there are many of them and not time to introduce all of them. And I don't think there's anybody participating in this meeting. So the number of people at Northeastern, at my university, and then we also have long collaborated with many groups all over the world. We also have many experimental collaborations, and I will, of course, cite things as I go along so that you will see some of that. So let me start by saying a few words about topological materials. You have undoubtedly heard about these in one form or another. They are, I would say, one of the greatest success stories for the band theory paradigm in crystals. Now, what is very surprising, to me at least, has always been, is that you know that the bands themselves have no physical meaning in the theory. So bands or these cone sham orbitals, they are only designed as variational parameters to get the total energy of a ground state energy of a system. Nevertheless, these spaghetti diagrams that you are used to, they seem to carry physics in them, enough of it that almost all the predictions that have been made successfully about, say, topological materials are really based on these types of diagrams, these types of bands. And there are all kinds of other things that have been done successfully based on these bands. Now, as far as I know, there are not too many examples in the history of science where you find that a theory can actually produce real materials that work in nature. So, in that sense, to my mind, this is one of the great success stories of theory. Now, some of you may not be quite familiar with what topology has to do with condensed matter systems. So let me just say a few words on that. Uh, Normally, we think of topology in terms of geometrical, mathematical uh, terms, and perhaps the simplest quantity that is commonly spoken about in mathematics is the shape of an object that can be coded in terms of its genus. Um, and by that one means that if one takes the Gaussian curvature over a surface and integrates it over the whole surface, then if the surface is closed, then its genus is defined as zero. You just sort of integrate the thing and do some uh, normalization and you get g of zero. Now this g will remain zero so long as the surface remains closed. If you have a hole like in a donut, then g will become 1. If you have two holes like in a pretzel, then g is 2 and so on. In that sense, this quantity g is an invariant. It captures the shape of the object at a fundamental level, irrespective of many details. So that's why it's a invariant. In the same sense, for example, if you have a soccer ball and you deflate it, it has no effect on its genus, on its invariant shape, the basic character of its shape. And in the same way, if you take a coffee cup, then you can pull it in, pull it out, and that kind of thing, and pretty quickly you can get a donut-shaped object. And so, in a topological sense, this coffee cup is the same as a donut. They both have the same genus in the sense that they have a single hole in them. Now, how all this enters into condensed matter physics can be perhaps seen in this very simple schematic diagram. So, if we have a bunch of atoms and we form a crystal and we separate them very far, then each of them will form a band. And each of these bands will be related to an orbital of the atomic system. And you see here schematically a red and a blue band, uh, colored lines, and they will generally have a gap. And this gap is a so-called trivial band gap in the sense that this gap can be closed easily and so on. If you now begin to bring these atoms together, that is, begin to reduce the lattice constant, then at some point these bands will begin to join at a node at a single critical point. And then if you further bring them closer, they could separate. And in this way, as it is shown, but now what you have is an inverted band gap. That is to say, this band gap is quite robust against many changes in the Hamiltonian. And this aspect of the band structures or of the quantum wave functions in a crystal can also be coded just like we did for the case of the surface of a sphere or a object through the Gaussian curvature uh, by taking the block wave functions and so on, and one can define a Berry curvature, so-called, and this Berry curvature can then be used to define a variety of topological invariants by integrating this over K space in an appropriate way. And a simple example is the so-called Chern number. But there are many such invariants that can be defined. And like all robust invariant things, these properties, this particular property of this band structure or of this wave functions is very robust against a variety of changes in the Hamiltonian. So it is in that sense that they are also topological invariants, and this is how the field has started. Now, what happens when you take two surfaces, here schematically shown that you have, so this Z2 invariant just simply is something that can take on two values. So it's sort of like having a sphere and a donut with 0 or 1 holes. And so when you have when you join together odd and even or even different types of topological materials at their surface, it turns out that there has to then be connecting states or boundary states, the various ways you can call them, they all mean the same thing. In particular, it turns out that in the case of insulators, so that even though the bulk band structure has a gap in them, when you consider the surface of these materials, so Z2 even could just be air, could be vacuum, then you are guaranteed to have surface states that are metallic. So that is kind of schematically shown here. Uh, so in the case of a trivial insulator, these states can be removed. But in the case of the non-trivial surface, they can't be removed. And so that's what schematically you see here, that I can either remove them altogether or I can make a gap by some small perturbations. But that is not the case with these non-trivial surface states. They also have very characteristic spin-dependent properties, these uh, metallic states that join the bulk bands on the surface, and that gives rise to many exciting properties. Now, these are controlled for most of the early work, time reversal based states. So let me walk you through a couple of slides here. So here I have shown a few examples of some of the uh, three-dimensional topological insulators that we have predicted successfully in the early stages of the field. Um, there are many, but I just mentioned a few here. The classic one is the bismuth selenide class of materials. That was among the very first materials that launched the field around 2009-10. Then many others followed. Here's the one we predicted on thallium-based chalcogenides. We predicted a whole class of them for ternary half Hoyslers. And these are still quite interesting materials. These femtenites and so on, 3 and 4 layered systems, controlled in various ways, is still another class, and there are many others. There was a milestone, a big milestone in the field, is the discovery that we made of the topological crystalline insulators. And notice the words here. So they're not just insulators, they're not just topological insulators, but they're also the word crystalline is put in. Now, at the time, I must say I did not fully appreciate the significance of this, but you'll see in a moment that this is a very key development. So what has happened here is all the insulators prior to this tin telluride class of materials, they were controlled only by time reversal symmetry. So the protection that was there in those states was only due to time reversal symmetry. But what we did here was to introduce crystalline symmetries in addition to this time resolve type of thing. So that was the new thing here, and uh, and what turns out now is that because these crystalline symmetries are so much richer than the time reversal symmetry, that leads to a whole new just an endless possibilities. And I'll say a few more words about that soon. Now, this class of materials, even today, even though these were predicted around 2012, 13, and successfully, and they are very well known, and there are probably tens of thousands of papers on this. And there are other materials that have been now identified as topological crystalline insulators. But this 10 telluride class, the very first one, still continues to be used for all kinds of things. And they have their unique characteristic properties. Another big milestone in the field, this theoretically in 2015, and it was pretty quickly verified experimentally. And this is the first Weyl semimetal. So everything before this is an insulator, but here the tantalum arsenide class of materials is the first single phase metallic material. It's a semimetal strictly, and it has Weyl cones in it, and it's a bulk system. So the topological states in this material now, for the first time when it was discovered, are bulk states, not just surface states. It also has very interesting surface properties, but this is the first material that was shown to successfully found that in fact shows uh, topological bulk behavior in the form of Weyl cones. So this is, of course, a huge, it is even now the workhorse of Weyl physics in terms of both basic and applications. But this really marks now a change in the way the field has then evolved. Now, soon after this, now, of course, things have really exploded. And there are many, many materials. I'm not going to go through anything other than one or two examples. Here is a room temperature Weyl ferromagnet that we found in 2019. And literally at this point, you can almost turn the question around. That is, and the underlying thing is what I alluded to earlier. Because the ground state of a crystal is very rich in terms of symmetries it has, in terms of orbitals it has, that it is excited. In principle, you can get all kinds of excitations way beyond what can be done in vacuum. So the vacuum can only create, Weyl Majoranas and the usual electrons and positrons, but there are no other excitations possible in the our physical vacuum. But in the condensed matter vacuum, that is the crystal vacuum, you have 200 space groups. Those magnetic space groups, they're even larger. So by the end of the day, you just have the possibility of creating double Weyls and multiple Weyls, God only knows what else. The question almost is that every material has topological, probably excitations. It's more a question of finding interesting ones. So that's where the field now has exploded. Let me give one exciting example in the last couple of years that I think you would enjoy hearing about, and that is the Axion insulator. So this manganese bismuth telluride system is the first Axion insulator. Now, axions are another, they don't occur in usual physics. However, in the case of these topological materials, you can have a strong E dot B field. That's the axion field. So E dot B coupling is normally not there in electromagnetism because there are no positive, there's no positive. So the end result is that we have a situation in which we could, in principle, control the magnetic properties using electrical fields only. And so in this material, manganese bismuth telluride, it's a layered material. The adjacent layers, so each layer is ferromagnetic, but the adjacent layers are coupled antiferromagnetically. And the axion coupling in this field is strong enough. So that was shown in this Nature paper, that when you using reasonably nothing very large electric fields, you can reverse the AFM state from this uh, on the state one to state two. So you see this blue thing has moved over there. More recently, in this 2023 Nature Materials, we have also shown that one can reverse the uh, AFM state with circularly polarized light. So, in other words, if you throw left-handed right versus right polarized light, you can change uh, the AFM order, reverse it as shown schematically here. So these are obviously have implications for applications and so on. And moreover, it turns out that these materials have very interesting quantum metric. Now, this is a whole new field that is evolving now. And in a few words, what that means is just like we define distance in ordinary space, with a ruler, centimeters, meters, that kind of thing. Similarly, we can define a distance or a metric between block states in a condensed matter system. And that metric, its imaginary part is the Berry curvature that I mentioned earlier. And normally there hasn't been much attention paid to the real part of that quantum distance, call it metric or distance. And now it's beginning to become clear that the real part of this quantum metric also plays very interesting roles. For example, it can lead to very interesting nonlinear Hall effects that were presented in this science paper and more recently in this Nature Electronic paper, and other properties, diode, and so on. So, anyways, this is all continuing to evolve. Let me also take a few minutes here to say something that has always been puzzling to me. That is, remember these things like Dirac cones and so on, these in the Weyl nodes that look like cones. That, of course, is the all talk of relativistic physics, special theory of relativity. And in special theory of relativity, one of the most common things that you hear about every day is the event horizons, light cones, that kind of thing. And I had always wondered whether how they will translate to the condensed matter physics, and that is discussed in this Nature Communications recent paper. Now, the physical origin of light cones and event horizons in special relativity is simply that the speed of light is uh, c is whatever it is, and that action cannot travel faster than speed of light. So these light cones and event horizons are really tied to just causality uh, in the nature. So similarly, this causality concept plays out in the case of the Dirac metals, semimetals, in the way it's kind of schematically shown here. It is much richer than in the case of free space, just like you have the vacuum of condensed matter physics. So here these cones can be, tilted. There can be more than one cones and all the rest of it. So by the end of the day, here again, what we find is that two cones cannot interact with each other unless they lie in this uh, event or in this kind of uh, in their own cones and dispersion cones. And the event horizon becomes a fuzzy kind of a horizon in the energy momentum space. Because remember, all these cones are not in real space; they are all in momentum space. So, anyways, this has some many interesting consequences. Now, let's see, how much time do I have? I haven't kept track of time. Hello?
Hello. Uh, you have 15 minutes more, sir. You can.
Hello?
Hello.
Hello, can you hear me?
Yes, yes, you are audible. Yeah.
How much time do I have?
No, sir, you will take your time to complete
Oh,
your. Yep.
thank you. But please stop me if I'm going over time. So let me say a few words about a few other interesting things that I think you will enjoy hearing about to the extent the time allows. So one very large field has to do with the high temperature superconductors. And this, of course, has a whole life of its own. But what is very interesting is that from the very beginning of this field back in 1987 type of a time frame, it became very clear early on that the usual band theory type of calculations fundamentally fail for these high temperature cuprate superconductors for their normal states. The reason simply is one way of seeing this was very clear early on is that the half filled system, such as lanthanum, say copper oxide, the band theory predicts it to be a metal, whereas the real material is an insulator. So when you dope this material and you get the superconducting state and so on, then of course there's not a whole lot you can do. Now there are ways of ad hoc putting parameters in that kind of thing to somehow capture parts of the physics of the doped system or other parts of it, but it is just not very predictive. Intrinsically, you're very limited in what you can predict. So what has happened in the last few years is that a new generation of functionals have come online, exchange correlation functionals have come online. Because remember, the accuracy or the reach of the band theory paradigm is fundamentally controlled by the exchange correlation functional that you use. And those functionals really haven't changed all that much for decades, except very recently. And these new class of functions, which go under the rubric of scan or various flavors of it, it turns out that they can capture the half-filled state of the cuprates correctly in the sense that you have the gap formation as well as the moment formation so that you are able to generate moment on the copper without any parameters. So there are no material dependent parameters in these calculations, in this modeling. So that, of course, means that you can have a whole range of materials that were completely outside the reach of the band theory. At least you can make some progress with them. So here I illustrate this with this simple example. So in the case of yttrium barium copper oxide, which is the original one of the original materials, soon after the lanthanum copper oxide. This for the oxygen 7 case, it's in the very much uh, in the superconducting regime around the top of the dome, superconducting dome. And what we found here is that we can, from first principles, get many stripes and uniform phases, many types of phases. I think there's something like 30 or so that we identified. And while there are all kinds of interesting things, but here there's one way of looking at these that is important to keep in mind. So what is shown here is the energy relative to the ground state AFM phase, antiferromagnetic phase, in MeVs per copper oxygen plane, uh, copper oxygen combination in the system. And you can see here all kinds of these 2D bond stripe, 1D bond stripe, and so on. And the total energy is shown as a function of the average copper moment, planar copper moment. And you see that the planar copper moment, even when you are in the ground state, it remains quite high. And certainly the non-magnetic state, this star at the top, that is lying at very high energy. So that guy is not relevant for any physics. But when you get down to the ground state of this material, you see there's just a whole bunch of very closely placed phases shown here in this blow up on the in the inset. And they differ only by a few MeV, as you see, 2, 3 MeV per copper oxygen copper atom. And all they involve, they're all antiferromagnetic spin arrangements in the nearby things with very high copper moment, 0.4 Bohr magneton. And the only difference in these various phases is that the phases themselves, the planes themselves, for example, are organized in different ways. You know, whether you follow a plane with the next plane being ferromagnetically or antiferromagnetically coupled, you know, that kind of thing. So the arrangements are only in how the spins are distributed past the nearest neighbors, but they all have nearest neighbor AFM arrangements. So the simple message by the end of the day here is that basically you can have many, many very closely placed phases in these complex materials. And that is very much the case in many other materials we have found. I've listed some papers here. You can easily find a lot more. And that is likely to be a very robust feature of complex materials. Let me also say here that band theory is not the answer to Cuprates. There are really fundamental things that it does miss. For example, the very way the band theory is constructed, you will never get in the ground state any excitation, lifetimes, and so on. But there are many other things that I don't want to go into here. But nevertheless, it does capture something right for the first time. Let me mention this example of what I thought was a very surprising result. It's a Nature 2023 paper. Now, what this has to do with is that when you look at photoemission from a surface, this is the Einstein's photoelectric effect in its modern incarnations. Usually you get secondary electrons. So you get primary electrons that are, of course, give rise to the usual angle resolved photoemission, etc. But you also get electrons that have gone through multiple scatterings in the solid, and by the time they come out of the surface, they are just scattered everywhere. So they are, you know, every which way they are going here, they are everywhere. And that is the normal secondary electron spectrum in any material. And that you see a whole bunch of materials here in this picture, and all these colored graphs, various colored graphs show you their secondary electron emission spectrum. However, it turns out the strontium titanium oxide STO surface, what we found is that the secondary electrons give rise to an incredibly coherent photoemission beam, unlike anything that is done by any other surface. So that is schematically shown here, and here you see this is almost like a delta function. It is really sharp, nothing like that in any other material. It's resolution limited, in fact. So this is just a bizarre effect, but even after, you know, whatever, more than 100 years of Einstein's description of the photoelectric effect, which got him a Nobel Prize, the reality is that the photoemission field just keeps throwing surprises at you. And this particular type of a behavior had not been recognized before, and there is no theoretical framework that can explain it, the existing theory frameworks. And we have a way of explaining it, but that's still under review, so I don't want to say too much about that now. In any event, what this does is it opens up a whole new field of quantum materials for photocathode designs. Most of the current designs are really based on the semiconductor type of materials, and they are pretty much reaching their limits now. But this now allows the possibility of going way beyond into new types of things. Let me say one or two words on this, another somewhat different thing, and that is we showed some years ago in the science paper 2011 that if you look at the deep inelastic scattering from a surface of LSCO, the different levels of doping. So, if it is undoped, then that's an insulator. Then when you dope it, it becomes a superconductor at some point, and then call it a dirty metal or whatever. Now, the interesting thing here is that it turns out that deep inelastic scattering or Compton scattering, it has this magical ability that, and that's well known, that you can really pick up the properties of the many body ground states. So in this two-dimensional material, what you're looking at in these three pictures are literally the maps of the dopant orbitals in the material, in this case, the oxygen dopants. Without worrying too much about technical things, you can see with your eyes immediately that this leftmost picture, rightmost picture, and this leftmost picture is essentially a momentum space image of the oxygen dopant orbitals in the low concentration regime. Whereas what is shown on the right is that in the overdoped regime. And this difference cannot be understood in any model in which you only have one orbital. This then was the first to then show very clearly that you need at least a two-band model, that is the dz square orbitals in this case also begin to play a role beyond the dx square minus y square orbitals of copper. So, and that at the time I thought was very interesting. But in the last few years, we have realized that this ability of these Compton scattering to essentially map the orbitals can also be used for battery material design. And that is a point that was
Sorry to
discussed in this
interrupt you, sir.
2021 Nature paper using LT, lithium, titanium, and the well-known battery materials.
Sorry
And
to
what we
interrupt you, sir.
found there is that basically in this way, and that's kind of shown in these pictures, we can essentially map at the atomic level the redox orbitals, the orbitals that drive the performance of a battery. And what that does is,
Sorry to interrupt you, sir. Uh,
yeah,
we have another session also, so please conclude in 10 minutes, right, sir?
oh, I will conclude it definitely.
Okay, sir.
It's okay. I'll conclude.
Thank you, sir.
So let me then just say a few more words on this. So basically what this does is now we are in a position to do a rational design of these lithium battery materials. So that has many implications, and we are pursuing them at various levels. I think I will just show one more slide, and then I will conclude in a minute or two, and I do appreciate your giving me a little more time. So this is another very large field that is now evolving. Everything we have talked about so far really has been bulk or such materials. But it turns out that these interfaces and when you take one type of a layered thing and put it on top of another, that creates a whole world of new possibilities, possibilities that are not easy to imagine with the bulk materials. So here is one example where and there are many such things where there's a tungsten disulfide film, and on the top of that we have put in bismuth selenide, uh, one layer, two layers, that kind of thing. And it turns out that the interface, this vacuum between these two guys, that creates a superlattice which is purely electrons. So there are no ions here because there's a vacuum, but it still gels into because of the way these potentials etc. work out, it actually gels into a real superlattice of just pure electrons. And the size of the superlattice can be controlled easily by just simply twisting these layers in different ways. So the net result is that you have a very controllable, purely electronic lattice. And that, of course, be used for all kinds of things. And but this is just one example. This thing also has very interesting gas sensing properties, this interface, and many other things. So this is just one example, but as I said, this is a whole new field. It turns out there are some other examples that I may or may not have mentioned here. Actually, some of these papers do, where it turns out that this interfaces can also stabilize phases of materials that cannot exist in ordinary ambient conditions because they have this environment that is chemically very different and that stabilizes all kinds of possibilities that are not possible to have otherwise. So I just thought I'll mention this before I conclude. So with those words, I hope so basically I have discussed some of our recent results in a wide variety of materials. The focus has mainly been in the work in the last couple of years. What would be a take home message? I guess I hope you'll agree with me that quantum matter will continue to offer us many surprises and functionalities for the foreseeable future. So let me just conclude here then, and thank you again.
Thank you very much, sir. Now, if anybody have query regarding, can so yeah, sir. We have one query. Yeah.
Very nice presentation, sir. You gives a very futuristic approach for the researchers. I want to ask a question. Uh, what is the limit of Jesus and churn number, and what parameters limits these parameters?
Well, I cannot make out anything, but if you can tell me what the question is, I can answer.
Sir, I am audible.
Hello?
Respected sir, I am audible.
You are audible, yes.
Sir, I want to know what are the limits for Jesus and churn number, and what parameters limits these two parameters?
Uh, which parameters, which two parameters were you referring to?
Jesus, G and churn number.
Genus. Yeah,
Genus, Jesus, genus. Okay, sir. Okay, sir.
yeah. So, I mean, genus by definition, if you have a object with 10 holes, then G will become 10. It's just defined that way. Now, churn numbers also can be higher order, and there are such materials around. Because, in the case of condensed matter systems, of course, you can effectively have nodes with more than just a simple charge like you would in the vacuum situation. So there is no limits as such. There just depends on the material, the number of orbitals involved and so on, the type of degeneracies. But typically, you don't get very high numbers because it's just the way the symmetries, etc., play out. So I don't know if I've really answered your question, but I
Okay,
don't know
thank
how
you, sir.
to answer better.
Thank you very much, sir. Thank you
Thank
for your nice presentation at this late hours in your university. We had a speaker, Professor Bansil from Northeastern University, USA. Thank you, sir, joining for us.
Well, thank you then. Good morning, you. So,
Thank you.
take
Thank you.
care. Bye bye.
Bye, sir. Now I would like to invite Professor Vivek Gupta ji for session this chair and Professor Ajay Nagar sir for session this chair. Our next speaker is Professor Pawan Kumar Kularia from JNU.
Good morning to all. Next talk is again it is online. So I request Professor Pavan Kulriya to start the talk. For the time limit for this talk is 30 minutes. Sir. Please. Sir.
So, good morning to all, and I hope, am I audible?
Yes, sir.
Yes, sir.
Yeah. So, first of all, thank you very much, Chairman, for introducing me, and I'm also thankful to Professor Sudhir and his team for inviting me in this prestigious conference. So, in principle, I love to attend this as a in person because Bikaner is just like my hometown. I have done my BSc from the Dumer College, but due to some other assignment, I could not able to attend it. So today I will talk about investigation of the phase transformation in the pyroclose structure material. So basically, we are working on area of nuclear materials, and in this talk, I will discuss few of our results. In that one, we have used information to be it can be used for nuclear energy application. So at School of Physical Sciences, JNU, I am taking care of this advanced material research laboratory, and in this lab, we are working on material for energy applications. So particularly, we are working in three areas. One area is nuclear material. So in that one, we are working in the area for designing of accident tolerance nuclear fuel for future nuclear reactor, as well as we are designing the material that can be used for disposal of high level radioactive waste that is coming from the nuclear reactor. So in today's talk, mainly I am going to discuss this material that can be used for disposal of high level radioactive waste that is coming from the nuclear reactor, and what is the importance of the phase change in that scenario. So these are the few publications that we got, and most of these results that I'm going to discuss in this presentation. Another area that we are working is high entropy alloy. So these are material are proposed material for structural of the nuclear reactor, like as a fuel assembly or a nuclear reactor vessel. And in these alloy, basically, you know that in case of stainless steel like that, so usually we take iron and then we are adding a small impurity of the carbon. So as a result of that, structure of the material will remain intact. But in case of the high entropy alloy, what we will take 5, 6 or more than that number of transition metal element, and then we make a alloy. So in the beginning, they have all different structure, and we will use arc melting or some other process technique at high temperature, and we try to make a single phase alloy. And that material, they are showing unique mechanical property or radiation resistance property. And another area that we are working is recently that we have started, that is in 2D material, particularly MXin that we are working it, and that few data that you can see. So you know that when we are talking about the nuclear reactor, so broadly that material for nuclear reactor that we can classify it in three categories. One material as a structural material, another material could be as like for nuclear fuel. So broadly these are uranium dioxide or thorium dioxide or plutonium dioxide. So these are radioactive material. And third material can be as a material for disposal of high level radioactive waste. So main problem that that nuclear energy is a very good source and clean source of the energy, but when we are talking about the spent nuclear fuel that is coming from a nuclear reactor. So if we take around 1 ton of spent nuclear fuel, so in our country we are using closed fuel cycle. So in that one, we will use some chemical process and by which we will separate this spent nuclear fuel various component. So that way uranium 238 we remove it, and then remaining is around roughly 50 kg. So in that 50 kg, it is containing fission product and trans-uranium element, and that is very complex in nature. And by mean of these chemical route, we are not able to process it. So now the question is that how we can dispose these out of 1 ton around 50 kg that spent nuclear fuel that is coming from nuclear reactor, and you know that lifetime of this actinide is very long. So from there, you can see this is a cross-section view of the fuel spent fuel pellet. So at the center of the fuel pellet, it is containing like fuel grain that is consist of uranium, actinide, lanthanide, oxide. And then at the grain boundaries, you can see it also containing fission gas like xenon, krypton, and iodine. And if you see the half lifetime of these gases like iodine, that 16 million years. So that way you can think like it is a very toxic, and these gases are continuously emitted in our environment. Same like that other lifetime is millions or billions of years. So that's why we need some strategy to dispose these toxic waste that is coming from the nuclear reactor, and what type of material that we can able to design it. So any material that we can propose for designing of spent nuclear fuel. So earlier people have proposed glass as a waste form or for disposal of this thing. So we can make the bricks of the glass, and that brick we can put it in deep geological site. But the problem with the glass is that if there is any acidic environment, so as a result of that, glass will be dissolved, and it may be possible like that it will contaminate the whole water table. So that's why glass is not a good solution for disposal of these radioactive waste. Then recently, there are some reports in that one it has been suggested like that why we cannot try with the ceramic like, and that ceramic is basically that that in our house that tiles are there. Okay, so they are made of the ceramic. So these are the oxide material. So any material that we can select for disposal of spent nuclear fuel, so it's supposed to have these property like because in last slide that I have discussed, like it is containing many different complex actinide. So it can be able to incorporate actinide of the various valencies. It's supposed to have high waste loading. It's supposed to have physical, chemical, and thermodynamically stable. Leaching resistance, in particularly in aqua environments, supposed to be very less. And most important is it's supposed to be radiation resistance, because you know that fuel will be disintegrated with the time. So as a result of that, alpha, beta, gamma particle fission fragment, they will be emitted. And due to these fission product, the mechanical property of this waste form will be disintegrated. So that's why we need some strategy like so various material ceramic has been proposed, and among them this structure ceramic, they found all these good property like they have good aqua durability, high chemical flexibility, high waste loading, and they have better radiation resistance, response, volume swelling is very low. And most important thing that in the nature we also have rock. From there we are taking this uranium and plutonium. So these rocks, they also have this pyrochlore structure, and they are in the nature for many years like that. So that's why we can think like that. Can we design these rock in our laboratory, and in that way we can again able to dispose it. So when we are talking about the pyrochlore structure ceramic, then radiation tolerance will depend upon what is the composition of this pyrochlore structure material. So basically, these pyroclore structure material is A2B2O7 type of material. So here A and B, these are the two cations. So A can be as like actinide or lanthanide. B is the transition metal. And these, if I will take the different combination of the A or B, so more than 500 different type of pyrochlore we can able to design it. So now question is coming that which pyrochlore that we need to take for this disposal of high level waste. And among another important thing is that these material, they also have very rich chemistry like that, because depending upon the cation size of A and B, these material, they are showing the different phase. So if the cation size A and B, they are almost same, like there is not much difference. So as a result of that, at A and B, they can easily swipe their position. And that's why the structure they will form, that structure is known as effect fluoride phase. Okay, so in that one means size of the A and B, they are almost same. And that way they can easily swipe their position and this structure will form. But if there is a large difference between the cation size of the A and B, so as a result of that, these material will form a highly ordered structure, and that structure is known as a pyroclore structure. And the stability of these pyroclore structure will depend upon cationic radii like Ra by Rb. If it is between 1.46 to 1.78, then only this pyroclore phase will form. And another important parameter that decides the stability of this parameter is this X parameter, that you can see that this oxygen is there. And so position of the oxygen will also decide the stability of this pyrochlore phase. And that will depend, that X parameter is supposed to be between 0.3125 to 0.03750. And then with the help of like radiation, temperature, pressure, and by changing the composition, we can easily change the pyrochlore to defect fluoride phase. Okay, so now as I mentioned is that 500 different type of pyrochlore that we can use it, or we can synthesize it. So which one we will study for the radiation or like disposal of high level radioactive waste? So for that, in these two paper, in the science and nature material paper, so in that one, that Sikafus has done some, they have done DFT, density function theory calculation. And on the basis of DFT, they have calculated how much energy required if I will swipe A to B site like that. So that is known as anti-site defect formation energy. So for a particular material, in that one, anti-site defect formation energy is very large. So it means like that swiping the position will be very difficult. Okay, so that's why these type of material he has proposed, they will be easily amorphized, and these material is not good for these type of waste disposal. But if the size of the A and B, they are almost same, like in case of zirconate, like here you can see, in that case, whatever energy that is imparted to the material due to radiation damage or like that, so that energy A and B position, and as a result of that, these type of material is expected to be a radiation resistance response. So I am a experimentalist. So we have synthesized these material in our laboratory, and then we have done radiation testing of these materials, how these material will be behave. So for synthesis of this material, we have used very simple technique, that is a solid-state reaction technique. So we material in the furnace, and then we do the processing at the various temperature. So in this one, what we have done is that we have taken study the effect of the composition. So we have replaced titanium with the zirconium. So Gd2Ti2O7. Then we have changed the composition of the titanium and zirconium, and finally gadolinium zirconium dioxide. So this one is electron microscopy study of this one. So that you can see, I have just replaced titanium with the zirconium, and then grain size that you can see. In case of the titanate, grain size is around 8 micron, and in case of the zirconate, grain size is only 2 micron. So just by replacing the titanium with the zirconium, I can change like from 2 micrometer to 8 micrometer. 4 times grain size I can able to control it. The reason for that is because if you see the ionic radii of gadolinium and so there is a large difference is there in between these two. And this phase will be formed at a very low temperature, like 1200 degrees centigrade. And in both the sample, we have done the processing at the same temperature, like 1400 degrees centigrade. Because titanate will form the phase at 1200 degrees centigrade, so it has enough time for the grain growth. Because grain growth will depend on two parameters, one is the temperature and another is the time. So in both the cases, we have taken the temperature and time in the same. But in this case, phase will be formed at a very low temperature, so it has enough time, and that's why titanate will be uh, smaller grain will be combined together, and it will form the bigger grain size that you can see. To further confirm the structural property of this one, we have done X-ray diffraction studies on these materials. So in next study that you can see, like as we are adding more zirconium, then peak is shifting toward the lower Bragg angle, and then we calculated the lattice parameter. And lattice parameter is linearly increasing as we are adding more and more zirconium. So the reason is very simple, because the cationic size of the zirconium and titanium, they are different, and zirconium has slightly bigger cation size. So as a result of that, lattice strain will be there, and that way lattice constant is increasing. Then another thing is that when we have done the ritual refinement of these data, and from there we have calculated the X parameter, the position of this oxygen parameter, and that you can see as we are adding more and more zirconium, then X parameter is increasing, and you can see if we change from 1.2 to 1.6, then there is a large jump in the X parameter is there. So what could be the reason for that, and can I use this one for explaining the radiation damage of these materials? So that curiosity that we have. Then to further confirm the structural property of this one, because X-ray diffraction can only give the long range ordering like that. If a perfectly crystal structure is there, then XRD is good technique. But we want to know that is there any short range ordering is there, and whether how much percentage of the phase of the pyrochlore and defect fluoride phase is there. So for that we have done Raman spectroscopy study. And in Raman spectroscopy, in case of the pyrochlore structure, these five mode are expected, like EG1, AG1, and 3T2G mode are there. And in case of the defect fluoride phase, T2G mode will be dominated. So that you can see like that in case of the titanate, we didn't find this T2G mode. And as we increase the concentration, that you can clearly see like that T2G mode will be observed. So with that with this structural and microstructural characterized material, that we have put it in the particle accelerator. So ideally, we supposed to do the neutron irradiation studies on these material, but you know that nuclear reactor time is very limited. Another thing is the neutron flux in the nuclear reactor. So flux that is present in nuclear reactor is order of 10 to the power 15, and if that flux is present reactor, but in fusion reactor, flux will be very high, and process temperature will be again high, and that that's why if we will use this material as a target for the nuclear fuel or as well as the disposal, so we need like some other technique. So in that one we can use the high dose. So that way particle accelerator is very important, because size of the ion is heavier than the neutron, and if the energy of the ion is quite large, so that way it will transfer very large energy. So the damage that we will do in 2 year or 3 year from the neutron, same damage with the particle accelerator we can able to do within 2 or 3 hours. So that's why we are using surrogate approach. So for that we have used this particle accelerator laboratory, particle accelerator at IUAC. And in IUAC, we have established in last few years this state-of-art facility like in situ XRD, high temperature radiation, and in situ microscope. In situ means like these facilities are in the particle accelerator beam line. So it means like in case of the X-ray diffraction, we will put the sample in the machine, and at the same, then we will irradiate with the high energy charge particle, and then we record the diffraction pattern. So that way, all the studies that we have done is on the same sample. So sample to sample variation is not there. So that way, the data that we are getting is more authenticate, and we can also able to save the time of the accelerator. Then another facility that is there in this beamline is high temperature irradiation test setup. So like we can put the material at around 1000 degrees centigrade, and at that temperature we can able to irradiate it. So like we can create a nuclear core reactor like environment in the laboratory, like, because the temperature of the nuclear reactor core present reactor is around 500 degrees centigrade, but in future reactor it will be around 1000 degrees centigrade like that. So that's why this facility is available. And once material is become amorphized due to structural disintegrity, so then another technique that is a micro Raman, so that will give the short range. So these three state of art facility that we have used for this thing. And detail about these facility you can find that these article that I published in Review of Scientific Instrument and Journal of Nuclear and NIMB, Nuclear Instrument and B. So in this case, we have irradiated with 120 MeV gold beam, and the reason for that is energy is almost same like fission fragment. And in this case, we have used this theoretical simulation. From there, roughly like electronic energy loss is around 25 kV per nanometer. So threshold for these material is around 20 kV. So this is the material that we have exposed it. First is the titanate. So in case of the titanate, this is the crystalline sample. And when we radiated like at a low fluence like 5 to 12, so that you can see. And it will be completely amorphized. This 5 to 12 means how much time that I am exposed the material to the radiation. So there you can see it will readily amorphize at a 5 to 12. Then we added more zirconium like zero point 0.4. Again, there is not much change. It is almost amorphized at the same fluence. Then we have added more zirconium like zero point 0.8 or 1.2. So there you can see at 1.8. Peak will still remain intact at a 5 to 12 fluence. But when we further increase the fluence to 1 10 to the power 13 sign per square centimeter, then you can see it will be amorphized. Okay, so same thing you can see. So as we are added more zirconium, like it is taking longer time for amorphization. So finally you can see like for 1.6 and perfect GD2ZR207. So in both the cases, we went to a very high fluence like 10 to the power 1 into 14 psi per square centimeter. But still this material will not amorphize. It will retain its structural integrity. So that way it is clearly we can say like whatever that is proposed by Sikafus and all as a theoretically like that. So titanate will be readily amorphized, but in case of the zirconate, it will take a longer time, and that way we can see like it is easily it is a better radiation resistance response as compared to the titanate. So to further understand what is the reason for that, we have deconvoluted this X-ray diffraction peak by using this one. And from that deconvolution, we have calculated the track size. So basically, uh, when this energetic ion like 120 mm gold that is bombarded on any materials, as a result of that, what they are doing is that this material will interact with the electronic system of lattice, because if you calculate the speed of this 120 mm gold ion, so it is a very high speed, like just like as the speed of the light fuse. So at that speed, ion will not interact with the nucleus. So at that time, because the speed of the electron is like Bohr-Weyl speed, so they are almost comparable. So that's why this ion will transfer energy to the electronic subsystem, and then later on these electronic subsystem will energy transfer to the atom or like that, and then atom will be displaced, and that way defects are created. And as a result of this one, some damage zone are created in the uh, system, and that damage zone we are calling as a latent track. Okay, so by using this X-ray diffraction technique, we have calculated the size of this damage zone, how much damage zone is created, and that we try to deconvolute it in this thing. So simply we have done calculated the area under the peak, then we have divided with the number of peaks. So that way we have calculated the amorphous fraction, and that you can see the amorphous fraction is continuously increasing, and then it will almost saturated at a high fluence. And in this graph, we have shown how this amorphous fraction is changing with the as we are changing the zirconium concentration. That you can see it is increasing, but in last two concentration, this amorphous fraction is almost zero. And further like that, in during the pristine sample, as I mentioned like that, from the refinement we have calculated the X parameter. So for X parameter that we have seen, it is linearly increasing, but these two composition last 1.6 and 2 perfect zirconium, the X parameter is very large. So that way, indirectly we can say like that X parameter can be also used, or we can control the X parameter, and by that way we can able to design the material. So any material that X parameter, particularly pyroprostructure, the X parameter is very large. So that material will show the better radiation resistance. So with that, this composition dependent study, we can conclude like that titanate is readily amorphized. where zirconate pyrocolor are relatively radiation resistance, and radiation stability will depend upon the ionic radii, and oxygen is also playing important role in these type of material. Then another study that we have done is that this is recently accepted in Journal of American Ceramic Society. In that one, that phase that we already amorphize, okay, and then we want to know that, for example, we want to record that phase. So whether it will be used the same procedure like that we have taken the initial integrate or some other mechanism. So in that one, we have done this one at Photon Factory, Japan. That experiment we have done in synchrotron in situ XRD, and there you can see like that this is amorphized material in all three cases, and then we have increased the temperature. So in the beginning that you have seen, when we synthesize the temperature, at least I need 1200 degrees centigrade to record the pyrochlore phase. But in this case, when titanate is 1.6, that you can see this material will be uh, convert from amorphous to pyrochlore phase at 1000 degrees centigrade. So it means like that when we are doing like high energy ball milling, or by that way we are mixing the material, and the material that is being amorphized from the ion irradiation, the mechanism of the crystalline process will be different. But in case of the pyrochlore, this material will be from the directly amorphous to pyrochlore phase will be there. But when the zirconate concentration is very large, so as a result of that, we went up to 1000 grade, but till that temperature, we didn't find any pyrochlore because this peak that you can see like 10 degree, this peak is characteristic peak of the pyrochlore. Other peak is they are like defect fluoride phase. So in these two material, we have seen like that my material will not change to the pyrochlore phase. It will remain in defect fluoride phase, and reason is that the size of the titanium, they are almost gadolinium titanium. That we observed is that this again in defect fluoride phase also depend upon the composition like that. So in this case, we have seen if the zirconate concentration is low, so in that case, the time that is temperature that is required for phase change will be relatively higher as compared to this thing. So this phase change again will depend upon the how much zirconium concentration is there. In last case, I have taken the gadolinium zirconium oxide, but in this time we have taken the niobium. The reason is that gadolinium is neutron poisonous, so it is not a good idea to use that as a nuclear fuel-like material. So in this case, we have taken the perfect niobium Nd2Zr2O7 and then non-stoichiometric composition, and these two we have calculate again. We have done the electrode refinement, and from their X parameter we have calculated it, and in both the material they are in perfect pyrochlore phase. That you can see these 10 degree, 15 degree peaks are there. And again, we have confirmed with the Raman spectroscopy. Only thing that we observed is that in case of the pure Nd2Zr2, a perfect stoichiometry phase, the peak intensity is large, so that is indicating like that it is better crystalline as compared to this thing. But X parameter in this case that you can see in case of perfectly Nd2Zr27 is slightly smaller, 0.3327 as compared to 0.3386. Then this material we have irradiated with the particle in the particle accelerator with 100 MeV iodine beam, and there you can see in case of Nd2Zr27 at a fluence of 5p13, it will amorphize. But in case of non-stoichiometric composition, that you can see it is not amorphized and peak will retain. So that's way it is clearly indicating like that if X parameter is large, then material will be not amorphized and it is better radiation resistance response. Then similar like that in last one that we have calculated the amorphous fraction and in both the cases, and from there we calculated the track size by using XRD, and that the other one. So from there we can find like that. So track size in case of non-stoichiometric composition, it is smaller as compared to a perfect stoichiometry. So that way the damage that is created in this one is smaller as compared to this one, and that's why it will be amorphized easily. Then another technique that to further confirm, because we can calculate the track size from the XRD, but that is an indirect observation. For direct observation, we have used electron microscopy, transmission electron microscopy, TEM, and in that one we have irradiated with a low fluence like 3 into 10 to the power 11. The reason for that is that low fluence ion will be well separated. So that way, this region you can see these are the damaged region, and from there we calculated the track size. And track size in case of non-symmetric composition is smaller
Hello, sir. Sir,
Due to
please.
smaller track size, this
Hello.
material will be take a longer time for amorphization, or we can say this is a better radiation resistance as compared to this one. Similarly, we have seen at a higher fluence also like that. So this ND2 ZR27, this will amorphize that ring, that structure you can see. But in this one, some
Hello, sir. Sir, please conclude in 5 minutes.
yeah, sure,
Thank you, sir.
sure, yeah. So then to know the local structure of this material, so how this coordinates and chemistry or like that. So for that, we have done genes and exhaust data at RRCAT Indore. And from there again, we have found like that this one is gens data at ND3 and zirconium edge. So there you can see like the position of the edge of this niobium is as same like ND2O3. So there is, so in that case, we can clearly see like that there is no change in the oxidation state is there. But when we done the exhaust data there, you can see, so as we have irritated, then the distance between niobium oxygen and niobium bond, they are changing. So that is again correlated, and these details that you can find in this paper. So then same thing, we have also done the phase recovery study, and this is matching with our earlier study on gadolinium zirconium oxide. So in this case, we have seen like that this we have gone up to 1000 degrees centigrade, but still again from the amorphous to crystalline phase is recovered, but it will not form pyrochrome phase. So this one is the last result that I will discuss. So in this one, we have studied the effect of the grain size. So you know that earlier two data that in that one we have used salt state reaction technique. So in that one we are using the process temperature around 1400 degrees centigrade. But in this case, the temperature that we have used is around 250 degrees centigrade. By chemical route we have prepared it, and then we have put the material in the furnace at a different temperature like 600, 1000 degree, 13 minutes, so that we can get a different grain size material. So these are the three samples that you can see from the XRD. It is a perfect phase like at high temperature treated, but S600 we didn't find any pyrochlore phase signature that you can see. Then these are the grain size from the SCM. This S600 is 50 nanometer, and 1000 degree treated is 106, and 1300 is 250. So further we also confirm with transmission electron microscopy. So same like order is almost same. And then we have done the Raman spectroscopy, because I mentioned in these two material like S1300, S1000, they are showing the perfect pyrochlore phase in case of XRD. But S600 phase, that is nanomaterial, that is not showing the pyrochlore phase. So for that, we have done the Raman, and in Raman that you can see all the modes are available for the pyrochlore. So that way all material they are in perfect pyrochlore phase, and then we have processed with the radiation damage. So like 15 nanometer, 250, 100. So there you can see when the grain size is smaller like S600, 15 nanometer. So this material will retain its structure at a very high fluence. So that way we can clearly see like that smaller grain size has a better radiation resistance as compared to the bigger grain size. Then we have done the like fitted this data by using a single impact and multi-step damage accumulation model by using this one. And from there we calculated the track size, how much damage zone is there. So when we use the direct impact model, then track size there is no consistency is there. But instead of that, we are using multi-step damage zone accumulation model. So in that case, in case of S600 smaller grain size, the amorphous region will be smaller, but as we are increasing, it will be increased. So further, we also confirm with the TM. So same thing like that in S600, the track size or damage region is smaller as compared to this one. So in summary, we can say like that when we use the single impact factor impact model, in that case, there is no consistency in the track size. But when we use the multi-step or damage accumulation model, in that case, the center part region is this one amorphous region, and outside region defectful, right? So with that, I will summarize my talk. So in that talk, I have discussed the irradiation-induced phase transformation in pyrochlore structure ceramic, and that phase transformation can be controlled by the composition, grain size, and stoichiometry. And another important thing that we observed is that anion lattice that is playing very important role, and by using the 48F parameter of the oxygen can be used to control the phase change of these material. Then we also done the thermal annealing to ignore the defect fluoride phase. But in this study that we have, in case of zirconate, this phase is not recorded, but in case of the pyrochlore, we have treated at 1000 degrees centigrade and we can able to get the perfect pyrochlore phase. So these are the my, so from the BRC, he's our mentor. Then Professor Vinita Gupta from science. And that composition dependent study that I saw, that work has been done by Dr. Saurav Sharma. Right now, he's the research scientist at Rensselaer Polytechnic Institute in USA. Then another part has been done by Dr. P. So right now he's faculty in some government college in UP. And this phase recovery part that is by the Yogendra Singh, right now he's doing PhD with me. And other are the other PhD students Vivek, Ankita, Goro, Anjuan. And this project has been funded by the Research in Nucleoside BRNS, and I'm also thankful to the IVC and FNL. So thank you very much. And at the last, I am also heading this institute at JNU Advanced Instrumentation Research Facility, because most of the students are there. So in this facility, we have all state-of-art facility like SEM, TEM, PPMS, XRD, NMR, and other technique that is related to the life science. So I request you, if anyone want to use, so you are most welcome and you can visit to our website. So with that, thank you very much to all of you.
Thank you, sir. We will have one or two questions from the audience side.
Yeah.
If there is any question. So, sir, once again, we thank you very much for your very informative talk. Thank you so much.
Yeah, so thank you very much.
So, next talk is offline by Professor Vinod Singh from Department of Applied Physics, Delhi Technical University. Sir, please. अपने pen drive में डालना है.
यूएसबी ड्राइव वो मीट बंद करना जरूरी नहीं वो ऑफलाइन है ऑफलाइन है क्या नहीं इनकी ऑफलाइन लेकिन बाकी तो ऑनलाइन चलता रहेगा ना सर ऑनलाइन जो ऑनलाइन जुड़े वो तो सुने नहीं जैसे कल किया था नहीं कल वो सब यूट्यूब पे ही चल रहा था कल इस पे नहीं चल रहा था यूट्यूब पे ही चल रहा है ठीक है इसको फिर मैं कैंसिल कल वाला मैं इसको एंड कर देता हूँ मीट वाला Thank you everyone for your pleasant time. Now we'll end this meeting for now. Thank you. ये रहा सर आपका इसका
So, Professor Vinod Singh will speak on gas phase synthesis of size-selected palladium and palladium carbon nanoparticles and their gas sensing applications. So Professor Vinod Singh has research interest in material science, sensors, 2D materials, nanomaterials and their applications. His professional experiences, he is Professor Applied Physics, Delhi Technical University since 2020. He is Associate Director also of Human Resource Development Center, Delhi Technical University from 2021 to 2023. He has performed various faculty roles at Delhi Technical University since 2003. He performed various administrative roles as convener, international conference. He has chaired many MSc admissions. He is member department research committee, purchase committee, board of studies. He has, to his credit, many awards and recognitions. He has a patent, a process for synthesis of metal core carbon shell nanoparticles, as well as multiple research excellence awards from Delhi Technical University. He is gold medalist in BSc and MSc. Various sponsored projects to his credit: AICT project, hydrogen gas sensors, etc., Delhi Technical University project, structural changes, etc. He has authored numerous papers on gas sensors, nanostructures, and optical properties, including work published in Ceramic International, IEEE Sensors Journal, and Materials Today. He has professional membership. He is a member of MRS, ACS, IAM, MRSI, IST, and ISC. Professor Singh.
ये कौन है क्या कौन भाई कौन है
सर वहाँ से आप माइक
नहीं, ये कौन है क्या
माइक के साथ
Good morning to all of you. First of all, I would like to thank the organizers for inviting me for an expert talk in this international conference. The title of my talk is Gas Phase Synthesis of Size Selected Palladium and Palladium Carbon Nanoparticles and Their Gas Sensing Applications. So in this slide, first of all, I will discuss the synthesis method, that is the gas phase synthesis method, in order to synthesize the metal nanoparticles and then metal carbon alloy nanoparticles. And in the part of the gas sensing application, I will be discussing the hydrogen sensing applications of these nanoparticles. So this is the presentation overview. As I said, in the first section, I will be discussing the gas phase synthesis setup for deposition of palladium and palladium carbon nanoparticles, for size selected nanoparticles and non-size selected nanoparticles. Then the growth mechanism of size palladium carbon core shell nanoparticles, and finally the hydrogen sensing applications. So the gas phase, if we see the gas phase synthesis system in the laboratory, it looked like in this way, which has various components. There is a spark generator, you can see here, where the nano agglomerates are generated. Then we have electrostatic classifier, DMA, differential mobility analyzer. This is very important part of this gas phase synthesis method. Then condenser particle counter, CPC, sintering furnace, and ESP, electrostatic precipitator. So the whole of the integrated gas phase synthesis system comprises of these components. And why it is said to be the gas phase synthesis method? The answer is that all physical processes related to the particle formations, they took place in the homogeneous gaseous method, gaseous medium. And therefore the name gas phase synthesis method. If you see that the particles are generated here in the spark generator and particles are deposited inside this ESP. So particle generations are taking place at a different place than the particle deposition. Therefore, we need some carrier gas in order to take the generated particles from the generation side to the deposition side. So in this experiment, we use the nitrogen as a carrier gas. Other steps can also be included in order to change the various parameters in between the spark generator and the ESP. So if you see the first component of this synthesis method, that is the spark generator, we have two electrodes. We have to take the two electrodes. If we want to generate the palladium nanoparticles, we took the both the electrodes of palladium. And if we use the palladium, if we want to synthesize the palladium carbon nanoparticles, then one electrode can be taken of palladium and other electrode can be taken of the carbon. So this is the method to get the only single metal nanoparticles or the metal alloy nanoparticles. So we have the electrodes here inside this spark generator. Some carrier gas is needed, as I have already told you. The nitrogen is the carrier gas, and outside when this spark generator, how it look like in the laboratory, you can see the electrodes are here, the metal electrodes are here, and the spark frequency and gas flow rate are the very important parameters for the gas phase synthesis system for this spark generator. So this spark generator, the role of the spark generator is to generate the primary nanoparticle in the size range of 2 to 5 nanometer. So we took the electrodes inside the spark generator, and the nature of the electrode depends on what kind of nanoparticles we want to generate. Whether the single metal nanoparticles we are generating, or our target is to generate the alloy nanoparticles. This is the another important part part of the system, gas phase synthesis system, that is said to be the differential mobility analyzer, DMA. And the role of this DMA is to classify the particle on the basis of their electrical mobility. And this is very important component of the gas phase synthesis system in order to select the size of the nanoparticle, because from the spark generator we are getting the nanoparticles of different size ranges from 0 to 1 to 100 nanometer. So if we want to generate the nanoparticles of 20 nanometer, a particular size, 20 nanometer, 40 nanometer, 60 nanometer, so then we have to use this part of the system, differential mobility analyzer. And if we see the schematic of this DMA, we have two electrodes, inner electrodes and outer electrode. We have to apply a very high voltage across these two electrodes in the order of the kilo electron volt. And the charged aerosol flow, this is the polydisperse. Polydisperse means the size of the nano agglomerates is means ranges from 1 to 100 nanometer. These are not the size selected nanoparticles. So polydisperse charged aerosol flow is the input in the DMA, and at the output you can see that the monodisperse aerosol flow we are getting from the DMA. So if we are getting the nanoparticles from nanoagglomerates from 1 to 100 nanometer from the spark generator, then after this passing through this DMA, we are getting a particular size nanoparticles. However, it has some size distribution. So the particles within a narrow range of electrical mobility, they are able to, only those particles are able to exit from this point. The particles having the higher mobility, that means the lesser size. Mobility is inversely proportional to the size of the nanoparticle. Higher mobility particles and the means smaller size particles, they will precipitate on this inner electrode, and the larger size particles will stick on this side. So we are getting a particular range nanoparticles from this DMA. So this DMA, differential mobility analyzer, is a very important part for the size selections, and we are getting a particular size nanoparticles. Another important parameter for this DMA is the mobility equivalent diameter, DMA. DMA is something different term than the nanoparticle size. Then if we include the CPC and some other parts like impactor, neutralizer into the DMA, it will make the electrostatic precipitator, this scanning mobility particle sizer, SMPS. So this SMPS consists of the electrostatic classifier and CPC, and the whole instrument, you can say here that this is the impactor, this is the neutralizer, and this one is the DMA, differential mobility analyzer, and this is CPC. So whole of this instrument means collectively said to be the scanning particle, SMPS, scanning mobility particle sizer. And the role of this SMPS is to measure the online particle size distribution. We can measure the online size distribution. We can see the online density of the particles by this instrument. And if we want to the size distribution of the size selected nanoparticle, we have to use the two SMPS. One is for size selection and second is for the online size distribution. When I say that the size selected nanoparticle, that does not mean that we are getting a single size nanoparticle. When I say that 20 nanoparticles, that does not mean that all nanoparticles are 20 nanoparticles, but we have a very narrow size distribution, maybe 19 to 21 nanometer. So this is the SMPS scanning mobilizer, and the role is to measure the online size distribution. Then this the final component of this gas phase synthesis system, that is the deposition chamber. This is said to be the electrostatic classifier, and we put the substrate inside this ESP. Substrate may be the silicon or quartz or solar cell or TM grid, depending on the application of the nanoparticles which we want to deposit from this gas phase synthesis method. So this is the whole of the schematic of the gas phase synthesis system. As I told that some carrier gas is needed, then the spark generator. From the spark generator, we are getting the nano agglomerates of different size and shapes. And then neutralizer, the role of neutralizer is to charge these nano agglomerates positively or negatively. Then this DMA will select only a particular size nanoparticles. Thus, as CPC can be added at any stage in order to see the size distribution. Then by the sintering furnace, particle are getting the spherical shape, and ultimately they will be deposited in this deposition chamber, which is said to be the electrostatic precipitator. This gas phase synthesis system can be modified in order to get the palladium carbon nanoparticles. So if we want to deposit the single palladium nanoparticles, we have to use both the electrode inside the spark generator as palladium electrode. And for palladium carbon nanoparticles, there are two methods to get the palladium carbon core shell nanoparticles. One is we can take one electrode inside this spark as palladium, other one is of carbon. But this method has some limitations. We cannot control. If we are using this method to get the palladium carbon core shell nanoparticles, we cannot control independently the core size and the cell thickness. But if we use both the electrode inside the spark generator as palladium, as you can see in this schematic, we are getting the palladium, both are the palladium rods. And to get the carbon, we have to use some carbon precursor. So we tried with different kind of carbon precursor, and we found that the methane is the best carbon precursor in order to get the palladium carbon core shell nanoparticles. So then we thought that at what stage we should add the methane in order to get palladium carbon core shell nanoparticles. So we optimized the instrument and found that this is the right place to introduce the methane before the sintering furnace. So we use the both the electrodes as palladium electrodes inside the spark generator. Agglomerates are generated. These are the palladium nano agglomerates of different size and shapes. They are charged, then the size selected by the DMA. And now at this stage, we are introducing the carbon precursor, which is the methane. So we introduced the methane of different concentration inside this nitrogen carrier gas. We took three different concentrations, 0%. 0% methane means no carbon is there, and therefore we are getting the palladium nanoparticles. Then we took 0.5% methane, and the sample synthesized is named as PDC 0.5 sample. PDC 0.5 sample means we are the 0.5% methane concentration inside the nitrogen carrier gas. Then the concentration can be changed to 1%, and the synthesized sample is named as PDC 1.0 samples. So three different samples are synthesized here. When no methane is there, obviously we are getting the palladium nanoparticles, single nanoparticles, single metal nanoparticles, and then 0.5% methane and 1% methane, which will lead to the formation of the PDC 0.5 sample and PDC 1.0 sample. So this is the integrated gas phase synthesis system for deposition of PDC core shell nanoparticles showing the formation of PD agglomerates in the spark generator, charging by the neutralizer, size selection in this DMA, exposure to methane gas of known concentration here, and then incorporation of carbon in PD lattice at higher temperature during sintering, compaction of agglomerates into spherical nanoparticles, segregation of carbon onto PD surface in the form of carbon shell, and deposition on a desired substrate. So this gas phase synthesis is modified, in fact, for synthesis of the palladium carbon core shell nanoparticles. And if we synthesize the PDC core shell nanoparticles by this modified gas phase synthesis system, we can independently, this very important, we have a patent on this, that we are able to control independently both the core size, inner part, and the cell thickness. This is very important for this PDC core shell nanoparticles synthesized by this particular modified gas phase synthesis method. So what is the growth mechanism for PDC core shell nanoparticles? As I said that we have a patent for this particular process. We have proposed the growth mechanism for PDC nanoparticles, and that process is patented by us. And this is the core shell formation PDC core shell nanoparticles which we proposed and then experimentally verified. So what we proposed in order to get the core shell formation for the PDC core shell nanoparticles, these are the PD agglomerates which are formed by the spark generator. Then methane adsorption. In the first stage of the core shell structure formation, methane adsorption happens. Adsorption of methane is the first stage on the PD agglomerates, and for it, the large surface area of PD agglomerates are important. Then in the second stage, the decomposition of methane. Methane decomposed into the carbon and hydrogen at PD surface, and it will depend on the catalytic reaction at the PD surface. In the third part, two things will happen. Incorporation of carbon in PD lattice at higher temperature during sintering due to higher solubility. Carbon is soluble in PD at higher temperature. It is not soluble at room temperature, but higher temperature carbon is soluble in palladium. So therefore, the carbon is incorporated inside the PD lattice. So incorporation of carbon will happen in the third stage at high temperature. Simultaneously at high temperature, what happens? Compaction of agglomerates into spherical particles. So in the third stage at high temperature, carbon goes in first thing, and the second is the whole of the particle will be getting spherical in shape. And in the final stage, we proposed in the final step, step 4, segregation of carbon onto PD surface in the form of a shell. So if we talk about the palladium carbon core shell nanoparticles, which particle goes inside in order to make the shell and which will make the core? So that will determined by the surface energy values. And the fact is that the carbon has a lower surface energy than the palladium. Out of these two, carbon has a lesser surface energy. Therefore, it will make the shell, and the core made of the palladium metal. So in the final stage, the segregation of carbon. Carbon incorporated inside the palladium in the third stage, and when it goes to the room temperature, remember that the deposition happens at room temperature. At high temperature, by the sintering furnace, the particles get spherical shape, incorporation of carbon, but the deposition after passing through the sintering furnace, the deposition happens at room temperature. There is no high temperature. So at room temperature, carbon segregate out from the palladium and it will make the shell around the palladium core. So this is the mechanism proposed by us to get the palladium carbon core shell nanoparticle. How the palladium and carbon core shell nanoparticles are formed. And this proposed mechanism then experimentally verified. We did the XRD for all these samples. In this slide, you can see that this is the X-ray diffractogram of PDC 1.0 nanoparticles of DM 40 nanometer. And we took the XRD at different temperatures. Two theta values and FWHM are shown here. At 300 degrees centigrade, we can see that the peak slightly shifts toward the lower 2 theta value. Lower 2 theta value indicates that it correspond to the lattice expansion. And this behavior is due to the PDC system where the incorporation of carbon results in the lattice expansion. So at 300 degrees centigrade, the incorporation of carbon is experimentally verified. As we increase the temperature to 500 centigrade, we can observe experimentally that the now peak is shifted towards the higher 2 theta value at 500 degrees centigrade. FWHM decreases, and this will correspond to the this will means the confirmation of the segregation of carbon phase from the palladium core. Further increasing the temperature from 500 degrees centigrade to 700 degrees centigrade, we can further see that the peak shifts towards the higher 2 theta value and decrease in FWHM also observed at 700 degrees centigrade, which shows the nearly complete segregation of the carbon from the palladium lattice. So what mechanism we proposed for the PDC formation, that is experimentally verified by this data, and that's why I said that we have a patent on this particular mechanism for the formation of PDC core shell nanoparticles. Here in this slide, the size selection of PD nanoparticles and nanoagglomerates are shown, and these nanoagglomerates comprises of the loosely connected primary nanoparticles of 1 to 2 nanometer size. Large surface area of these nanoagglomerates are very important in order to absorb the methane on these sites. Here the temperature effect can be seen as we increase the temperature from room temperature to 200, then 400, and then 700 degrees centigrade. We can see the process of the formation of the spherical nanoparticles from the various size nanoagglomerates. Okay. So these two slides are important. How can we control the core size and thickness independently? And in order to control the core size, we have to change the DMA voltage. And there are two parameters. One is the DMA voltage and second is the methane concentration. You can see that if you put the methane concentration constant here, 0.5%, and if you change the DMA voltage from 0.6 to 2.5 and then 5.4 kilovolt, then the result is we are getting the nanoparticle core size as 11.1 to 21, 29.6 corresponding to these different DMA voltage. So if you change the DMA voltage in this table, you can see that the core size is changed. And because the methane concentration is constant, you can see that the cell thickness is constant here. So how can we change the core size? By changing the DMA voltage and putting the methane concentration constant. And these data are obtained by drawing the size histogram. We took the nearly 200 nanoparticles and calculated the core size and cell thickness and then formed the size histogram, and then these values are calculated with some standard deviation. This plus minus figure shows the standard deviation of these values. And then how can we change the cell thickness? Control on the cell thickness, that can be done by putting the DMA voltage constant. Two parameters are there, DMA voltage and methane concentration. So if we put the DMA voltage constant and change the methane concentration, in this way we are able to change the cell thickness. You can see that the size of the nanoparticle core remains constant, whereas the cell thickness changes from 0 to 1.7 to 2.1 with some standard deviation. So by changing the DMA voltage, we are able to change the core size, and by changing the cell thickness, we are able to change the changing the methane concentration, we are able to change the cell thickness. So these are the, I won't have to skip these effects. Then we made the hydrogen sensors based on these particles, palladium and palladium carbon core shell nanoparticles. We designed these four different kinds of the sensors, where PDC deposited on the silicon wafer, palladium deposited on silicon, palladium carbon deposited on the graphene, and palladium deposited on the graphene. We studied the sensitivity, response time, and recovery time for all these designed sensors, and the result is that as we increase this, the formula for the sensitivity is the resistance in the presence of hydrogen, resistance in the presence of nitrogen, and this is the formula to get the value of sensitivity these sensors. The net result for all these sensors is that As we increase the cell thickness, the sensitivity increases. This is the main observation for these all four sensors. So when PD is used, it does not show any sensitivity. PDC 0.5, 2% sensitivity is observed. PDC 1.04% sensitivity is observed. So by increasing the carbon thickness, we are able to get the higher sensitivity for the sensor. And similar effect is observed when the palladium and palladium carbon are deposited on the graphene. PD deposited on graphene, we are getting 0.8% sensitivity, and PDC 1.0 deposited on graphene, it shows 6.2 sensitivity. So in both the cases, both kind of sensor, when palladium carbon deposited on silicon or palladium carbon deposited on graphene, for both cases, as we increase the carbon concentration or the cell thickness, as we increase the sensitivity increased, and further the response and recovery time also improved. So these are the sensing results, as I have told you. This is the final conclusion that the size selected. Remember that this method is not limited to only palladium or palladium carbon. It can be extended to other metals also, like silver carbon or platinum carbon or copper carbon. For those particles, the same method can be used. So size selected metal carbon core cell nanoparticles are synthesized using an integrated gas-phase synthesis system. More importantly, it allows the independent control of the core size and cell thickness. This very important result of our experiments. And then PD cells having a higher sensitivity and faster response time and recovery time in comparison to the bare palladium nanoparticles. And these parameters further improve with increase in the cell thickness. So this is the result about sensitivity. As we increase the carbon cell thickness, the sensitivity increases, and as well as the response and recovery time improves. So this is the workforce behind this experiment in the nano fabrication laboratory at Department of Applied Physics, Delhi Technological University. Thank you.
Thank you. So we have 1 to 2 questions from the audience side. If there is any question from the audience.
Very nice presentation, Professor Vinod Singh ji. There are three parameters you are focusing: DMA voltage, concentration of methane, third is temperature.
Yes.
When you are changing the concentration, you are taking constant temperature.
Temperature is optimized for every size, different size. For different size, if for 20 nanometer DM, the temperature will be different. For 40 nanometer, temperature is different. So first of all, we optimize the temperature. If we are getting the 20 nanometer, remember that the temperature is different for different DM values. We have optimized. This is our first stage to optimize the temperature.
My second question is that in your experiment, how much voltage is possible and what is the limit of voltage for your experiment?
For DMA, the broad range for the voltage in DMA is kilovolt. So mostly 1 kilovolt, 1.2 kilovolt. These are the values for the voltage applied across the electrode inside the DMA. The voltage values are given for the three different sizes. Just see these values. In order to get the 20 nanometer size nanoparticles, 40 nanometers, see the first two columns in this table. We are getting the mobility equivalent diameter values as 20 nanometer, 40 nanometer, and 60 nanometer. And the corresponding DMA voltage values are 0.6 kilovolt, 2.5 kilovolt, and 5.4 kilovolt. So these are the ranges for our studied samples. Samples of DM values of 20, 40, and 60 nanometer. Ranges from 0.6 to 5.4 kilovolt.
My question is that when you are increasing the DMA voltage, size of nanoparticles is increasing.
Yes.
Sir, we can discuss in tea time, please, sir.
Yes,
We will have
definitely.
next talk now.
This is the result that as we increase the DMA voltage, the size of the synthesized nanoparticle increases. If you put the methane concentration constant, then cell thickness remains constant. So the inner part increases by increasing the DMA voltage 20 to 40 to 60, but cell thickness cover that remains same. That will be decided by the methane concentration. That is the important factor. The cell thickness is determined by the methane concentration, whereas the core size is determined by the DMA voltage.
Thank you, sir, for
Thank
your very informative talk.
Thank you very much.
Next speaker for this session is Professor Anami Bhargav. Yeah.
We invite Professor Vinod sir for a memento.
टॉप लगा दीजिए हाँ HDMI है ना हाँ HDMI है ना ठीक है है क्या इसमें यस ये लगाना पड़ेगा
स्लाइड हो जाएगी
मैं खुद ही कर दूंगा यहाँ से नहीं कोई नहीं मैं यहीं से कर दूंगा मैं कहीं से कर दूंगा यार मेरे ये
Hello.
वाला पास वाला
Now
वो पास वाला यहीं से
we invite Professor Anami Bhargav from Department of Physics, Government Dungar College, Bikaner. He has a long research experience in nanophotonics, and he has, to his credit, 8 PhD, 100 plus research papers. He is a visiting research fellow of ICTP Italy, and he is a landmark for the research activities at Department of Physics, Government Dungar College, Bikaner. Please continue, sir.
Thank you, organizers, for inviting me to this talk. Hopefully, I will try to wind up my lecture within the stipulated period and try to justify for the short duration which was provided to me to prepare this lecture. Hopefully, the lecture basically it's not it's some the work which we have done at the Government Dungar College. We set up a small lab, nanophysics lab at the college, and this is one part of the research carried out by few scholars on the photonic crystals using the properties of photonic crystals for optical biosensing. And most of the applications we have proposed here, they have medical applications. So these are the contributors. Dr. Bhuvneshwar Sutar, who is also the convener of this conference. Dr. Sapna Dinodia, she is assistant professor at the Polytechnic College, and Dr. Ankita, she is also assistant professor in a government college. So main contributors to this, I am just monitoring the work
What is the purpose of doing this kind of research is the basic physics which we generally process, and the processes which are uh, we are already studying, like light technologies related to optics, illumination, imaging. And then we have electrical technologies, like we have transformation and wiring, and a separate branch for electronics where we have switching, amplification, and modulation of signals. So when you talk of using photons, and a new branch comes up, which is just photonics, which is the application of photons to light matter interaction, and using photons to control light. So light controlling light. That is, so the same processes which happens in electronics uh, behaves similar to the processes in photonics, which is amplification, optical switching, and then color changing. And why? What is the purpose? Basically, the technologies fields which are in operation, and which will play a major role in the coming years. And presently, also a large development is taking place. That's what communication is a large part. Transportation, traffic, medicine, and then you have new materials coming up for the design of devices and materials. And then there is a problem of environment, which is still going on. We are facing it from the social media, power production, and then so photonics generally comes from photon, and it is just the generation, process, and manipulation, as I've told you. It's the photon to certain function which we want to achieve. And nanophotonics is something which we apply to nano level, and the devices which formed, they are either wavelength or sub-wavelength scales, where the behavior of materials and devices drastically change respect to the physical, chemical, and structural nature of the uh, matter. Now, what this field holds for different fields in the technologies and research. So we have physicists, which can design nanocavities, study optical phenomena. You can generate single photon sources. Then we have nonlinear optical processes, which are well known even in optical fibers. And then you have nano control of interaction between the electron photons and phonons, which are the carriers in materials, semiconductors. For chemists and chemical engineers, you can have different processes for processing the nanomaterials, molecular structure, supramolecular assemblies, then one-part synthesis, which is very contributing these days, and then drug production. Device engineers, there's nanolithography, which is still going on, fabrication of the photonic crystals and micron and submicron devices. Then you have integration, photonic crystal circuits, microcavity devices, and quantum dots and quantum wires. And for biologists, also this field hold good regarding the genetic manipulation, because the DNA are also of the nanometer size. And then you have bio-inspired photonic materials which change color, and you have biotemplates for photonic structures. Then you have bacterial synthesis, also artificial, using the photonic materials. Uh, in biomedical researching, uh, this has a very important role, and we are using the last of this, which is the nanotechnology for biosensors. The other are light guided medicine and light activated therapy, which is still development going on for devices, and diagnostic techniques. So we are concentrating here for the nanotechnology for biosensors. So how do we do it? We are using a specific form of material called the photonic crystal, which is a periodic dielectric structure. And then what it does is, when a light interacts with the matter at the wavelength, at the sub-wavelength levels, it is affected by the periodicity, and there anything break with the periodicity gives rise to a strong dispersion, curves, which give rise to frequency and propagation direction depending on the dispersion created in the labs. So similar to the semiconductors, we have photonic band gaps. How do they do it? These are two master papers which rationalize the photonic crystal field. One is 1987, localization of light by Axion, and the second is 1987, inhibition or spontaneous emission. And this those two papers gives a purpose how to confine and we can control light with light. So there is the whole new devices which have come up now at the macro and the nano scale devices. This is the composition how the semiconductors and photonic crystals they up to scale they are similar in working. Uh, in semiconductors we have atomic scales, but here the length is similar, is corresponding to the wavelength, and these are artificial structures, and electron flow is basically controlled, but here we control the electromagnetic wave itself for the propagation and use. So how this PBG is created, band gap similar to a semiconductor, there is a valence and conduction band as we know, but here you have a reflection in the two periodic materials, and the reflection and the transformation generated give rise to the scattering processes, which give rise to the value of eigenvalues in the transfer by calculating diagonalizing the matrix. So this is the method. We have the electromagnetic wave propagation in the z direction, and the matrix is calculated just by placing parallel layers and calculating the component. There's a phase change across the boundaries, and this give rise to this photonic band equation, which we solve normally, and then the results are obtained. What this process looks like is we have periodic structures separated by a center defect layer, basically. And if we don't have a defect layer, you'll have no state is present, which is shown here in this first diagram. And then as the defect is introduced, their localized states are generated, they come up, and there is a allowed frequency which is shown with these small. Secondly, also, if the thickness of this defect layer changes, then also there is a shifting of the resonate peaks within the forbidden gap, as shown in this diagram for transmission. And these boundaries are basically the band gaps which are generated. So we have localized states which we can control, and then they can be used for further processing. Similar the structures, if we change the composition of the material, because materials is very important, the property which we choose, it must be thermally stable, it must be structurally stable, because the light it interacts, and it not only polarizes, but it interacts strongly with the field of the material. So any change in the material concentration, material property, or the response with the light changes the property of the uh, uh, material and the device which we are going to form, or the sensor which we are proposing right now. This is the synthesis mechanism. How does it work? It is just by, so what we do is we draw transmission spectrum, and we alter the periodicity or the refractive index uh, using the different structures or the materials, and then even the light signal can change the property of the transmission spectrum. Then two things we have to calculate. One is the quality factor, which determines the sensor property, and it should be high. It is just defined as the resonant frequency divided by the change in the frequency due to the change in the refractive index. And second is the sensitivity of the device, which is thus the change in the wavelength divided by the change in the unit refractive index of the material or the defect. These are the biosensors which we simulate in this work: malaria detection sensor. And there are three versions of it which we have studied. Then another is the hemoglobin concentration, and one is another for tuberculosis detection, which uses the film. And last two is one is poliovirus, which is uses a waterborne like sewage water, and the last one is bacterial detection sensor, which is just a modified form of the for the tuberculosis detection, which is also a bacterial infection. So malaria is a parasite thing, and hemoglobin blood is used in all the samples majority for determination of malaria and hemoglobin. So how do we do it? For forming a malarial diagnostics sensor, we are using a 1D photonic crystal periodic layers of AB format and a central defect layer, which is generally the blood sample of the infected RBCs. And malaria has 3-4 stages of leading to increasing infection due to the parasite, and therefore this this device uses two layers. One is the silicon A, and this B is just the silicon dioxide. We need oxide layer, oxide material, because it has got a higher refractive index. So lower frequencies can be concentrated within the material, while the higher frequencies can be concentrated in the low index material. So the hemoglobin concentration, we have used the formula which is used by the diagnostic labs, and the data, some of the data is also taken from the diagnostic labs, which they are processing from the patients. So this is something which we obtain. There's a transmission, depends on the wavelength. The standard wavelength used is 800 nanometers, which these diagnostic labs are using for probe of the blood samples for malaria and dengue right now is also giving alarming result. So what we notice here is that the refractive index and the wavelength, they are strongly correlated, and there is a linear dependence. So you have a very high sensitivity which can be obtained, and this work can be used to design a very fast response and high sensitivity with good quality factor, which we can see it is for a normal stage, but it as the stage progresses, the refractive index goes on decreasing, and the wavelength also increase. So you have a quality factor which is around 10 to the power of 5. So it's quite a resonate peak, which we can, although the FWHM is slightly large, but the resonant peaks are quite high, and there is a shifting of the peaks with respect to the normal stage of the malaria. Now, this malaria has a special property that once it is a person is infected, uh, it due to the bite of the Anopheles mosquito, uh, this leads to many changes in the biochemical and structure units. Basically, the level of the infected RBC, this parasite Plasmodium falciparum, multiplies, and therefore it contributes to the change in the refractive index of the material, which is the blood sample. But there is another uh, basically it's an enzyme. It's called hemozoin, which contributes to the low value of the refractive index, and it is very difficult to observe with a simple microscopy with the diagnostic labs are using. So with this technique, this hemozoin changes can be clearly measured because the wavelength varies linearly, and it corresponds to a very small design of the sensor, which is just 11 microns approximately. And the time lapse, the difference between the two settings can be of the order of a femtosecond. So it is the device can be ultra compact in size with very fast response. Now, this is the basic detector which we simulated, and then we improved on this detector for using a different geometry and different material. Like with a defective, we have placed two metals layers around it, and what happens is when a light signal propagates through it, it gives rise to two phenomena. One is in the bulk, and another is which is at the surface. It's called the surface plasmon resonance, SPR. And what happens is this give rise to a entirely different process of detection. And what happens is we treat this material, what we have taken to be homogeneous initially, and also isotropic and non-magnetic, so that there is no interaction with the. And for this, we have to neglect the complex part of the refractive index. For this, we have to take a material which has an extension coefficient very small or negligible compared to the at that wavelength. And therefore, the change which occurs in the refractive index can be correlated for the obtaining the results. So the basic geometry is something like this, where the relations for refractive index, we have used different relations. And then for the metal, it is the Drude model, which is available in the Kittle's book. So it's a simple geometry with simple values and relations, which give rise to a wonderful phenomena. For silver, like metal, if we introduce silver, which is the most non-reactive of all the metals and very stable for the design of devices. So what happens is, in this case, the input signal frequency give rise to SPR, which excites it. And what happens is there is a loss of energy due to the interaction of the electric field, and there the transmission decreases as compared to the normal PBS article. And although the peak is decreased, but FWM uh, although still not significantly affected, but the peak, the sharpness of the peaks improved. So we have a better sensor and with a large sensitivity for all the stages which we have. We can see here the wavelengths, they are keep on increasing, and the quality factor is also increased significantly. If we change the thickness of the layer, which is due to the infections or the infected material, then and changing something like 7 microns, then the sensitivity can be improved up to 100, 104 compared to the 700 something in the normal uh, sensor. Uh, and similarly, if the incidence angle of the incident beam is increased from around 80 degrees, so we have maxima, which is attained at 83, something like 86 degrees. So that will give rise to wonderful phenomena of with less transmission, but sensitivity is increased. So that is the second one. We have improved this sensor also with another layer, which we have introduced with the replacing the metals with the a double negative metamaterial. Uh, Metamaterials basically they are materials with periodicity or randomly distributed artificial structures, and they have the property that size and spacing. Okay, so spacing which is very much less than the wavelength of the incoming electromagnetic radiation. So you need very high plasma frequencies, so which are available if you insert this layer, then plasma frequency can be generated with a very high value of something like 10 raised to 14 hertz. And so the sensitivity can be improved further with reduced transmission. Again, it can be improved from 1100 to 1400 nanometer per REU. So, and this last one, I will just wind up and skip the rest of the part for the polio virus and other thing. So this was the last biosensor which we have introduced, the nanocomposites. And now nanocomposite has another property that you can generate large number of localized states within the structure, because the metal is dispersed on a homogeneous matrix. Here we have taken two materials. One is TiO2 and another is SiO2, and we have changed their fill factor, that is the material diameter to the total lattice constant. So that fill factor, if you change, then these sensors can behave significantly in a different way. The transmission peaks, they are shifted, and then we have this final result that the you have sensitivity which is increasing for all the two, and quality factor is also significantly improved up to 1400 for Ag doped SiO2. But it is the Ag doped TiO2 which steals the show with better performance, although the transmission is low, but you have still good FWHM and wavelength switches. I think I skip all this hemoglobin concentration, which we have done. Uh, Another which we have calculated is for tuberculosis detection, and it is in conformity with the diagnostic data which is available in the lab, and it has a better sensitivity, no doubt. And similarly, there is one work which we have done on the waterborne bacteria using a graded, like if the thickness is increased, then how this bacterial infection gives rise to a better sensor. And another work is for poliovirus, still, although it is eliminated, but in some other countries in Africa and even Pakistan, poliovirus is still alarming stage. So this is basically depending on the sewage water analysis, and where the defect is replacing the water treated, which is contaminated water. Even from the taps, you can have this. And there are peaks which are generated, and that's all. This work we are not going to say. So these are the conclusions that one can generate these photonic crystals using these standard materials with properties without violating the laws of physics, and preparing. This is the interface between the physics, biology, medicine, and chemistry. So, and material science, of course, is the most important part of this detector sensor. I think I've concluded as per the wishes of
Thank
the.
you, sir. Very informative lecture.
And thank you again. Dhanyavad.
And any questions?
1D photonic crystal. What is the difference between 1D photonic crystal and photonic quantum Weyl structure? Number two question is, what are the criteria for choosing the materials?
Second, what I think second question. Ah, 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 yes, yes, yes. Material selection is basically done for using three components. One is mechanical stability, which is structural units, uh, which we can choose using the periodic table, like the outer shell elements. Second thing is thermal stability, because light generates heat. So within the material, it should be thermally stable. And third is the extinction coefficient, which is the absorption of the electromagnetic radiation with the material. So these three criteria decides the material. We cannot choose every material for the, except that the contrast of the refractive index must be large. That is one criteria.
Thanks, sir. We shall continue our discussion.
Thank you, sir.
And
Thank you again, sir.
please uh, facilitate with the memento.
मैं आप लोगों को बताना चाहता हूँ कि ये जो वर्क है, ये बेसिकली हमारे भुवनेश्वर सुथार के द्वारा कंट्रीब्यूटेड है। और ये जो पुरस्कार है, ये जो थैंक गिविंग किया है, ये एक्चुअली इनका बनता है, क्योंकि ये एक ऐसे व्यक्ति हैं, अभी बीकानेर में रह के इनका स्टैनफोर्ड यूनिवर्सिटी की लिस्ट में 2% ऑफ द वर्ल्ड साइंटिस्ट में इनका नाम आया। एंड MNIT से सिर्फ 5 लोग हैं, एंड राजस्थान यूनिवर्सिटी की में आज की तारीख में कोई भी नहीं है जो प्रेजेंटली एम्प्लॉयड लोग हैं। सो राजस्थान में बाकी यूनिवर्सिटीज में भी लोग नहीं है। सो ही बिलोंग्स टू दैट 10 पर्सन्स फ्रॉम राजस्थान जिनका की नंबर ऐसे में आया है। तो ये उन्हीं के लिए बनता है, मैं रिसीव कर रहा हूँ उनके बिहाफ पे। थैंक यू।
Our next speaker is Dr. Dev Arastu Pancharia. He is a polymath, a theoretical physicist, cosmologist, and mathematician. He is working as a faculty in RNB Global University. He is the youngest elected fellow of the Royal Society for Encouragement of Arts, uh, Manufactures and Commerce, and a member of British General Council other than science. He is particularly famous for his thought-provoking public lectures on wide-ranging areas. His recent book, Einstein and the Evolution of Quantum Physics, From a Light Beam to Deep Cosmos, became a global bestseller in just 2 weeks. The book is now available in 50 plus countries. His recently published research, edited by prominent American physicist and father of quantum gap, Dr. Mark George Kurzik, Chair of Physics and Astronomy at Washington State University, has resolved a major long standing mathematical problem in quantum information theory and quantum computation. The statesman has referred him the smartest man alive, and British magazine Eastern Eye has quoted him in the league of some of the best brains in history. So please, Professor Arastu.
No, I won't have any. It's strange, but I know I don't have any presentation. You have a presentation? No, I will just speak.
It's a wonderful experience. I'm perhaps the most youngest one you will be hearing. And trust me, they say that scientists are mad. And you are currently seeing the maddest person. So that's how it is. I know it's ironic, but the conference is on applied physics. Uh, Unfortunately, or perhaps fortunately, I don't work explicitly in applied physics. I work in theoretical physics. My work is to understand the nature of reality, and my work is to romanticize the nature, to understand the universe. However, since I don't have any presentation, I'm sorry, because there are two fundamental reasons. One that I got to know about that I'll be speaking today just last night, so I could not. And another reason that I know it might sound provoking, but I think presentations make you a weaker scientist. I'm sorry to say, but that's how it is. Your mind has to be the best PPT ever. So that's what I think. Today I'll be speaking about my recent work in quantum computing. So they say the recent trends. I think this year's Nobel Prize in Physics went to John Hopfield and Geoffrey Hinton for artificial intelligence. So we see that the trends are going in the direction of something with which we have not imagined a few decades earlier. Quantum computing is one of them. So I'll speak in a way that you can connect with what exactly it is. I'll be trying to as less technical as possible uh, for you to understand things. So because I'm sure that physics as a subject is so vast that it's not possible for everyone to get expertise on everything. So quantum, so your computers that you see at your home are the classical computers. They work on this fundamental that were bestowed by Alan Turing, the British mathematician. Uh, he published this work in 1936 about a mathematical formulation that has even led Britishers to win the World War II. So, so on that principles, we have the idea of bits, and out of those bits, these days you have computers and supercomputers. Now, in 1982, there was this physicist Paul Benioff. Paul Benioff has studied the superpositions within the framework of Alan Turing. Now, superposition simply, as we all know, it's two things at the same time. It's the weird word of quantum, so we have to deal with it. And that very framework of Paul Benioff has introduced quantum Turing machines because it has fundamentally described the Hamiltonians within the states in regards to the mathematical formulation that has been given by Alan Turing back then. After that introduction of quantum Turing machines, it was a major breakthrough and sort of a starting point of what today we have, the quantum computers. Within that Paul Benioff's framework and the frameworks that carried on after that, we have some powerful mathematical computational abilities that harnessing the quantum mechanical laws and making the quantum computers that are being done by IBM and Google these days. So, but since we all know that mathematics is the language to communicate uh, in physics, so and also let me make it very clear that mathematics is not science. Physics is science. Mathematics is an art. So mathematics is this logical structures. But mathematics has been wonderful in communicating through reality. As Eugene Wigner once said, the mathematics has this unreasonable effectiveness. So there are certain mathematical limitations, and one of those mathematical limitations within the framework of Paul Benioff and other people, what we today call as the penalty problem. So penalty problem is one of the most uh, you say these hot topics, hot strange problems within quantum computing mathematics. The penalty problem is about so I'll give you a very brief example of it. So in classical computers you have 0 and 1 as bits. In quantum computers you have qubits. So qubits are fundamentally when 0 and 1 as two states are existing at the same time, they are manipulating at the same time. So for 1 bits you have one classical operator. For 2 bits you have two classical operators in classical computation. However, in quantum realm you see that this operations are exponentially increasing. So for 1 qubit you have 2 quantum bits, and for 2 you have 4, and so they are drastically increasing. For 10 you have 1024 quantum operations. And if I say that if I go up to 50 qubits at the same time, you will have roughly the number of quantum operations as 1.25 multiplied by 10 to the power 15. So it falls somewhere between a quadrillion and quintillion. So it's a pretty large number. However, if you see closely, that for 10 qubits we have 1024, which is I think 4 to the power 5. And for 50 qubits, which is the largest qubit quantum computer we have in present in physical time, it is roughly around 4 to the power 25. So now we see these patterns in 4 to the power some n, where n is the number of qubits. And penalty problem says that, and these are the quantum operations that relies for their computational abilities, for what we call complexity in a technical term. So in complexities, we often see that the penalty parameter, which is often described by P, is always less than or equal to 4 to the power n. Now there comes the mathematical issue. The mathematical issue is, if P is always lesser than or equal to 4 to the power n, it means we will have a lot of limitations mathematically to make the most powerful possible quantum computer in the world. And that's where mathematicians come in. And as there is this famous saying that mathematicians are those people who can turn a coffee into a theorem. So mathematicians arguably are romantic people. They formalize structures that sometimes don't even mean with the reality. So mathematicians came in to solve this strange problem, and it's been nearly 4 decades since we have physicists and mathematicians are working on it. In quantum computing, as I suggested, these quantum operations, they have this linear exponentiality, which is called the linear complexity. And the framework of quantum computing as of now is more dependent on the linear combinations of forms. Now, when I encountered this problem, I thought that we might approach it with a different way. So I approached it in a geometric way. So by geometry I mean the treatment of manifolds and the treatment of differential geometry, algebraic topology, and these kind of things. So I have looked at it in a different way. I have utilized the representation of what we call SU2n, the number of qubits, because since we are dealing with the quantum mechanical forms, so we are certainly involved into the more complex world. It's not the real world. So SU2n, because we have the intrinsic Riemannian metric, and Riemannian metric is fundamentally isomorphic state into SU2n. So we endowed a manifold on SU2n, and then I won't be much technical here, but then treating those manifolds, I have figured that there is a way to cope up with this problem, and the way is to uh, substitute the linear complexity with geometric complexity, because in geometric complexity you instead of relying on numbers, you rely on the structures that are embedded in within quantum states. So that's, I think, that has helped me. And then I thought I worked on the problem for a couple of years, and I personally thought that I might have arrived on the solution. So I sent it over, and it was some strange revisions, and eventually it got published. So it means the problem might have resolved, but we have now new limitations. So now within my work, we extended this limitation that P can be greater than or equal to 4 to the power n. So it is a geometric way of looking at things. So this is, I think, in recent advancements, it's quite rare to speak about those things that you personally have contributed. So it's been a privilege for this power to able to contribute into things. So this was it. I know, look, time is a quite important conceptualization for physicists. So I understand the value of it, and we have already been running late. Moreover, I dealt with problems that are more closer to the universe in quantum field theories, quantum gravity. We are searching for a quantum theory of gravity and quantum cosmology. So I work upon these fields. And in mathematics, sometimes because it helps, so I deal in higher dimensional topology and knot theory and other things. So these have certainly helped me to contribute meaningfully recently in the quantum computation. This was my recent work, so I just thought to share. And I don't have the presentation, as I said, but I hope I've been able to do justice with what I have said. And in the scientific realm, I think the conferences are now, specifically in our country, as becoming agathocacological. And but it's wonderful to seeing that professor people like Professor Vivek and uh, mm, uh, other Professor Suthar and other people are contributing quite meaningfully. I'm extremely glad. I'll have to leave for Kolkata today as only. So I would have missed this opportunity to see all such great people. I'm sure we'll be able to speak sometime on theoretical physics as well, in particular, because we have higher chances of winning a Nobel Prize. Thank you. Thank you very much.
Thank you for your very informative saying about quantum computing. So I think this is the last talk of the session.
Thank you, Professor Vivek Gupta ji and Professor Ajay Nagar sir, for chairing this session. We have wonderful presentation in this session. Now our third invited session is over, and after the lunch we have two more talks at 2 o'clock. So please gather here at 2 o'clock for the invited session. Uh, Up to that time, you can uh, go to the poster session and have the lunch. Thank you all.
Check, check.
हेलो लैपटॉप का पासवर्ड बताना लैपटॉप का पासवर्ड
So good afternoon, participants. You are once again welcome to the post-lunch session of invited talk. May I request Professor Anami Bhargav to kindly come on the stage and carry out the session as chairman of this invited talk session. Respected sir. Mic. देशमुख सर पहले जैसे परिचित हैं उनको
Hello. Welcome all the participants and the speakers of this session. We are going to start this session with the first talk by Dr. R. Deshmukh. He's professor in the Department of Physics, Institute of Chemical Technology, Mumbai. And he has research interest in the plasma technology, polymer physics, functional materials, biomedical applications of plasma treated surfaces, electro-optical properties of polymer dispersed liquid crystals, polymer nanocomposites. He did his PhD 2002, and he has a teaching experience, a long duration, and courses taught include solid state physics and undergraduate engineering and chemistry. He has also guided PhD students, about 9, and some of the notable projects and contributions he has. Book authored, one book chapter also. He has one international patent pending, and so I invite Dr. Deshmukh to present his talk. You have 30 minutes. and 5 extra minutes for discussion.
ये बंद कैसे ये ना ये पॉइंट रहेगा हाँ लेफ्ट उल्टा उल्टा अभी सुनिए ठीक है Good afternoon, everybody. This is, am I audible? They are last. Okay. So this session is after the lunch, and the job of speaker becomes very difficult, particularly if we have good food, including sweets. Anyway, so today I will be talking about pulse plasma surface modification for biomedical applications. I belong to the Institute of Chemical Technology, Mumbai, which was established in the year 1933, and the first director was a British. And I belong to the Department of Physics. We have physics department caters teaching for BTech and MTech courses, as well as we have our own MSc program, MSc Physics. This is the outline of my presentation. I will talk about basics of plasma, then continuous wave plasma and pulse plasma. Few examples of controlling film chemistry using pulse plasma. Traditionally, by varying some plasma parameters, people have controlled film chemistry, but the extent of change in film chemistry with those parameters, varying those parameters, was limited. With this pulsing mode of plasma, we achieve wide range of surface chemistries. Then I will talk about enteric coating done using pulse plasma polymerization, and then I will be presenting few case studies. So what is plasma? If you look at the screen, you will come to know that solids have a very regular and periodic arrangement of atoms, molecules or ions. At the most, these atoms can vibrate about their mean position, so their position is fixed. When we supply energy, solid is transformed into liquid. Liquid molecules slide over each other. They have little more freedom as compared to solids, and they take the shape of the container that you know in which they are kept. Then if you provide further energy, it is transformed into gases, and these gas molecules are energetic. They are separated. Distance between these molecules or the atoms, gaseous atoms, is far apart. And further, if you provide energy, maybe in the form of heat or electric field, then these gas molecules are ionized, and then what we get is basically ions and electrons as an ionized gas. If it is a gas which is there is singly ionizable, so as a thumb rule, you will find equal number of ions and electrons. So by considering the energy of particles constituting it, plasma is energetically the fourth state of matter. And here in the diagram, you can see two scales are there, x-axis scales. One is the temperature scale and the other one is the particle energy in electron volt. So plasma is having normally 10⁴ to 10⁵ Kelvin temperature. And on the particle energy scale, the energy is around 1 to 10 electron volt, which is sufficient to carry out most of the chemical reactions and surface modification, surface etching, surface cleaning of polymeric and textile materials. So By definition, plasma is the fourth state of matter consisting of ions, electrons, UV visible radiations, and there could be some neutrals, because not necessarily that all the gas molecules will get ionized, or there will be recombination of ions and electrons turning into the neutrals. So broadly, this plasma can be classified into two. Thermal equilibrium plasma, basically pressure is more than 10 torr. It is called as a thermal plasma. And at high temperature, the gas becomes ionized, fully ionized, and there is sufficient number of electron and other neutral species which are there in the chamber, plasma reactor, and because of sufficient number of collisions between energetic electrons and other constituents of it, so there is a transfer of energy from electrons to the plasma species, and thereby the electron temperature is around same in the ballpark as that of the ion temperature. So they are of the order of 10 raised to 4. And since it is a hot plasma, it is used in cutting, drilling, welding, or even creating scratch resistant hard coating like thermal plasma spray coatings. The other thing is cold plasma. It's not cold like ice or something, but relatively as compared to hot plasma, its temperature is around room temperature, and here only 1 to 10% of gas molecules are ionized, and therefore there are less number of electron and neutral species in electric collision, which results in insufficient transfer of energy from electrons, and therefore the electron temperature is quite high, 10 raised to 5, and ion temperature is around room temperature. So we don't feel that it is hot. The reason is the size of ion, if you compare with the size of electron is 1 by 2000 times smaller than ion. So we don't feel that electron temperature, and therefore it is called as a cold plasma. And you know, DC RF glow discharges, neon lamps, ionosphere, aurora that you see at polar regions are the examples of this kind of plasma. Atmospheric pressure plasma, cold plasma can also be created. We have dielectric barrier discharge, corona, microwave plasma, plasma torches also. And these are tissue tolerable plasmas where, these plasmas can be employed for wound healing application or any other in medical fields. In laboratory, it is achieved by applying high voltage. It can be either AC or DC. The frequency can be very high, like 13.56 megahertz. We call it as RF plasma. Microwave plasmas are also created. And at my institute, ICT, we have 4 or 5 different kinds of plasma reactors that we have developed, and we use them depending upon the nature of the work. And we have, atmospheric pressure plasma systems, also vacuum based plasma systems. Then plasma torches are also available that we use. Traditionally, to change surface chemistry, people have varied system pressure, type of monomer or the type of gas, their flow rates, distance between two electrodes, substrate biasing, so on and so forth. But here our approach is variable duty cycle pulse plasma, with the help of which we will be able to vary surface chemistry to a greater extent. Why we want to change surface chemistry is that surface chemistry plays a very important role. And remember, material interacts with surrounding through surfaces only. And this surface chemistry is important for transforming hydrophilic surface into hydrophobic and vice versa, or for biomolecules immobilization, or creating surfaces, okay, which are biocompatible, suitable surfaces for cell growth, proliferation, adhesion, drug delivery, creating non-fouling surfaces, creating highly antimicrobial surfaces. There are so many applications of surface chemistry. So now I will talk about what is pulse plasma. So basically, for certain milliseconds, plasma is on, and for certain milliseconds, plasma is off, and this cycles continues. So when plasma is switched on for certain milliseconds, so there will be generation of active plasma species. and the population of active plasma species increases as shown in this diagram like a sawtooth waveform. And when we switch off plasma for few milliseconds, so obviously this active species plasma concentration will decrease, but still there are active plasma species in the off state also, and that can lead to surface modification. During off period, monomers fragmentation is avoided, etching of surface is also avoided, so we get better smoother film enriched with functional group, and deposition rate is increased. The reason behind it is that the etching is avoided in the that off time, whatever the millisecond it is. And to maintain a good deposition rate, the next plasma on pulse should arrive before the population of active species goes to zero. So the basically duty cycle is what plasma on time divided by plasma on plus off time. This is the comparison of pulsed and continuous wave depositions under equivalent wattage condition. So this shows that if we carry out deposition at peak to peak power 150 watt and 10 millisecond off and 50 millisecond off pulse if it is there, then the effective power consumption is only 25 watt. So as far as the energy requirement is concerned, okay, this is energy saving kind of thing. So for some task we wanted to have polymeric film having higher refractive index so that it will scatter wave in a different direction. And therefore what we did is we selected dibromomethane as a precursor monomer so that bromine containing film will be there, and bromine as such in the form of a gas also it is having high refractive index around 1.6, and that's the reason why we selected dibromomethane as a precursor monomer. And here you see that for continuous wave deposition in the graph, the deposition for 10 minutes when it was carried out, the deposition was only around 30 nanometers. But as we increased off period, we kept on period 10 millisecond constant, and the off period was varied like 10, 25, 50, 100, 200 like that. So as we increase the off period initially, the deposition rate increased because the etching is avoided, and the depositing atoms get sufficient time for the lateral movement also, and thereby you can see that the films are smoother and smoother as we increase the off period. Now this slide shows these are XPS spectra. This shows that for continuous wave, the first diagram, continuous wave, you will find a good concentration of carbon atoms in aliphatic carbon atoms, C single bond C, and less carbon attached to either single bromine or two bromine atoms. But as we increase the off time, okay, 10, 25, 50, 100, 200. So with progressive increase in the off time, the retention of monomer functional group, in this case, bromine atoms attached to carbon, okay, that increases, and thereby, you will find that the bromine to carbon atomic ratio, okay, that increases systematically as a function of increasing off time. And since the bromine content in the film is increasing, which results in increasing refractive index that you can see in other diagram. The refractive index for continuous wave deposited film is 1.7, and it increased to more than 1.9 something. So even any change in refractive index in the second decimal place is also considered as substantial change, and here we have got a very good change. So by controlling film chemistry with the help of pulse plasma, we can have films having different refractive indices. For some other applications, we wanted to have, or we wanted to control the degree of hydrophilicity, and for some other we wanted excellent hydrophilic film. So for that purpose we selected allyl alcohol as a precursor monomer, and then the deposition was carried out by in the pulsing mode. So 1 millisecond on and 2 millisecond off, the lowest one in FTIR, and then we kept 1 millisecond on period constant, and the off period was varied from 2 millisecond to 30 millisecond. So the off period allowed us to avoid fragmentation of monomer and retention of monomer functional group, which is OH group. So as we increase the off period in the FTIR diagram, which is highlighted in green, that you can see the OH component is increasing. So OH is responsible for hydrophilicity and CH is decreasing. Okay, if more CH content is there, hydrocarbon, it is hydrophobic. So CH content is decreasing, and the immediate effect of it is the measurement of contact angle. You can see that the contact angle decreases continuously when we increase the off period in the depositing film. So sequential change in duty cycle leads to large scale progressive change in film condition or film chemistry, where all other plasma parameters are kept constant. For one more application, we wanted to have a good number of carboxylic groups onto the surface for human endothelial cell growth, adhesion and proliferation. So we initially we selected bare tissue culture plates in the graph that you can see here. Okay, so the population of the cells was limited, and then we varied carboxylic group content from 3.6 to 6.2 to maximum 9% on the surface, and for 9%, of course, this was possible because of change in duty cycle suitably, and when we could incorporate around 9% of carboxylic groups on the surface, that yielded a good number of cell adhesion, growth and proliferation of human endothelial cells. So that was about the film conditions. But in plasma, we have developed a 360-degree rotating vacuum-based plasma where we can functionalize nanoparticle. We can attach specific functional groups like OH, carboxylic, amine, halide, epoxy, like that, for various applications. And this is environment-friendly technique where no harsh acidic medium like H2SO4 and HNO3 is used. So for that purpose, we developed this 360-degree pulse RF plasma. This is schematic of it, that there is a provision that we can pass gases or we can pass some monomer vapors also into that. And this is the actual photograph in my laboratory of 360-degree rotating plasma. And then in the next slide, you can see actual picture of that plasma, the upper diagram, that is rotating reactor, and it is a vacuum based. Still the vacuum is maintained, that you can see. And we have created 3 protrudes on that cylinder, so that at each and every rotation, the nanoparticles or submicron size or micron size particles are taken up and they freely fall into the reactor, so that all the sides are equally treated. And just to give you some idea about the pulsing nature of plasma, that flickering that you can see in the lower diagram, that flickering is basically the pulsing. For certain milliseconds, plasma is on. For certain other milliseconds, plasma is off. So we use this 360-degree rotating reactor for enteric coating on nano or submicron size drug particles, powder particles, using pulse plasma polymerization. What is enteric coating? Enteric means small intestine, and enteric coating means it is a barrier or a coating applied to oral medication to prevent the release of drug before it reaches to the intestine. Of course, the path is through stomach only. So this coating will be intact in stomach, and when the drug particles go into the intestine, that coating will be removed. So that is called as enteric coating. And enteric coating works by presenting a layer on the particle which is stable at highly acidic medium. The pH of stomach is around 2. And when that drug particle enters into the intestine, where the pH is different, 6.5 around, relatively base as compared to the stomach. So when there is a change in the pH, this coating should get removed. That's the basic idea about enteric coating. So why enteric coating is required? There are 3 aspects of it. To protect the stomach from the drug. What is this? Basically, non-steroidal anti-inflammatory drugs, if they are they are taken continuously, basically painkillers, without the advice of doctor. If you take it continuously, it can hamper stomach lining. Stomach has a lining because it's a very acidic medium there. So to protect the inner side of the stomach has some lining, and this non-steroidal anti-inflammatory drug etch out that lining, so it can create ulcer, multiple ulcers, some, okay, and it can bleed also if continuously painkillers are taken. And therefore one need to protect, the drug, okay, interacting with the stomach lining. So this is called as a protection of stomach from the drug. The another aspect is to protect the drug from the stomach. Some of the drugs, when released in the stomach, can cause discomfort or nausea, or that drug molecule itself gets damaged. One example I will cite here, omeprazole is a drug which is normally taken if you have acidity. But when this omeprazole is released in the stomach, it severely gets damaged. It has to work to lower down the acidity, but if it is getting damaged, it means that you need more amount of omeprazole. Certain amount of it is going to waste, and certain amount of it will work, right? So the dose is increased. So therefore, for such cases, it is necessary to protect drug from stomach acid. And another thing is to release the drug after the stomach for cost effectiveness purpose. It means that sometimes we need to take some supplements. As we go old, you may not get all necessary nutrients. And if this supplement, what you take, nutraceuticals, if is getting hampered or damaged in stomach acid, maybe say 50% is getting damaged. So you are paying say $100, but in return you are getting only 50, right? $50 out in return. One more example I would cite here is L-glutathione is extremely important for cell health. Basic building block of our body is cell, group of cells is tissues, and then further, right? So cell health is the utmost important thing. And for the good health of cell, L-glutathione micronutrient is necessary. Whatever we get through vegetables and all those things, that gets severely damaged in stomach acid. So we totally rely on our liver to synthesize L-glutathione. But you know that as we age, the functions of all parts is going to down, right? So similarly, the capacity of liver to synthesize L-glutathione also decreases, and we don't get good amount of L-glutathione, which is very much necessary for cell health and overall body health. And therefore supplements are given L-glutathione. But again, it is damaged. So such drugs are to be enterically coated for cost effectiveness also. And currently, it is not that first time I am talking about enteric coating. Enteric coated medicines are there in the market, but current scenario is that tablet is made first and then the enteric coating is offered, or the drug powder is put into the capsule and the entire capsule is coated. What we are projecting here, we coat each and individual drug particle first and then is filled into the capsule, or then the tablet is made. And this is more meaningful than entirely coating the tablet or the capsule. Many of you must be knowing ecosprin. The active pharmaceutical ingredient is aspirin crystal. That aspirin ka goli both logon ne liya rahega, but now it is ecosprin. Since it is enterically coated, so the name is ecosprin. Now you see the ecosprin is a very small tablet, right? And original aspirin was a quite big tablet. But since it is enterically coated, its bioavailability is more because it is directly delivered to the intestine. There is no damage in the stomach, and therefore the lesser amount of aspirin crystal drug is required. and therefore the ecosprin tablet is very small. So by offering such enteric coating, we save the drug and we increase its bioavailability. Bioavailability means the how much quantity of the drug is actually available to the body. If say 70% is available to body and 30% goes to waste, so bioavailability is 70%. So if we are able to put this kind of drug, okay, which gets damaged in the stomach acid, okay, and 100% into the intestine, so we increase bioavailability few folds like that. So that's the basic thing. So there are certain criteria for enteric coating, that when such enteric coated drug enters into the intestine, it should disintegrate within 12 minutes. Otherwise, if it takes too much time, that will pass through intestine, will not be available at all for the body. Similarly, this enteric coating should remain intact in the stomach acid minimum 2 hours, because that is the residence time. So that coating should be intact. And there are some other factors also that one need to consider. And then we offered this plasma polymerization technique, because traditionally whatever we do, okay, they either coat entire tablet or the capsule is coated. So here we coat individual particle and then we made the tablet or something like that. So in order to visualize how this enteric coating works, we carried out one more experiment. We coated red dye particles with that kind of coating, and then we put it into the acidic medium to see the effect. And the purpose of selecting red dye particles is that even if suppose 2% of the dye particles are not coated, it will show some color. Or if the coating is non-uniform and coating has say some cracks or some voids, still there will be leaching of red color. And therefore we selected red dye particles for this, just to show you the how it works. So in 2 beakers, the pH is same as that of the stomach, that is around 2 pH. And in the measuring cylinders, we have kept a buffer solution, so that when it is added into the beakers, the pH is changed to that of the intestine. And let us see how it works. On the left hand side, it is uncoated dye particles, and on the right hand side, it is coated. And we are testing it rigorously. It's a magnetic stirrer. Okay, that kind of movement is not there in the stomach, but we are testing it rigorous condition. And now when we add a buffer solution into it to change pH, on the right hand side you can see that when the pH is changed, the coating disintegrates and releases the dye molecules, right? So this was just for visual, uh, to visualize how it works. So we have published this article in Journal of Drug Delivery Science and Technology. Of course, this work was carried out with the help of pharma people in my institute. So we selected omeprazole drug. So omeprazole, and then we put into the plasma. So we offered coating onto that. In the diagram, that coating is shown with brown color, and then you can see the tablet made there. Okay, microsphere. Oh, sorry. The tablet is made here. Oh, it's not. Yeah, you can see that. And when such tablet, okay, is taken, so what happens? Individual particles get separated in the stomach itself. If the entire tablet is coated, the entire intact tablet will go to the intestine. We don't want that. We want all the particles to be separated in the intestine, and each particle is having coating, so that from stomach to the intestine, one by one those particles will enter into the intestine. Intestine will have a sufficient time to absorb them, and the release of drug will be over extended period. So it is a control release as well. And here you can see that for the pH, which is same as that of the stomach, uncoated particles, they release immediately, whereas the coating is, less than 10%. And here, when we change to the buffer, you can see the release rate is increased. So here we use graded index films, okay, different duty cycles, and we could do that. Okay, I can skip this. Okay, this is contact angle of, you can see that this tablet and this tablet, the difference. Okay, but I can skip. Similarly, we carried out drug release kinetic study also for different duty cycle, and bare crystal of aspirin is released immediately, and for the pulse 1/5 means 1 millisecond of 5 millisecond on this, you can see the pink colored, and when we change the duty cycle, you can see the profile is different. So by controlling the duty cycle, by adjusting the duty cycle, you can adjust flow drug release rate. This is another piece of work where we
Sir,
Yeah.
sorry to interrupt you.
Okay, I will finish fast.
Okay,
Okay.
5 minutes.
So this is another piece of work where we increase the solubility, thereby we increase intrinsic dissolution rate, and hence the bioavailability of poorly water soluble drug. Of course, majority of the drugs which are being synthesized, around 40% of them are poorly water soluble. Their aqueous solubility is limited or practically insoluble in water. And there are methods to increase their solubility. The one physical method is go on reducing the particle size. Solubility you can increase, but the quantum of increase in the solubility is still limited. Another way is convert that active pharmaceutical ingredient into its salt. And you know that all salts are soluble in water. But when you convert it into salt, sometimes, or in most of the cases, that salt is not having the same medical value. Means it will not work as a drug then. Then what is the use of converting it into salt, right? When it is not going to work as a medicine. So therefore, what we did here is we employed pulse plasma, oxygen plasma, where the on time was very small and the off time was more, so that the effect of plasma on the activity of the drug is not compromised or not hampered, but we increase its solubility rate. And there, so what we did is we selected this ritonavir drug. Ritonavir is an anti-HIV drug and is practically insoluble in water and aqueous fluids. So its oral absorption is limited because of its solubility. And with the help of plasma, we increase its solubility, thereby increase it. It means that the drug quantity going into the body will go down. So side effects in that proportion will come down. And at the same time, we can satisfy 4 patients because the quantity of the drug requirement is low. So, and why we selected this? The reason is basically since the beginning of this epidemic, 75 million people have been infected with HIV and 50% of them have been died. So this is a very grave problem. So we address this using pulse plasma surface modification. So we had kept certain objectives before that, and then we use pulse novel plasma technique for enhancing solubility. And since it was related to medicines, so the material was characterized by n number of techniques, and we found that its medicinal value is intact. So for untreated, yes.
Could you please find out?
Yeah,
2
3
minutes.
3 minutes. So for untreated, the solubility was 16 microgram per ml, and for plasma treated, it increased to 94 microgram per liter. You see how many folds we increase the solubility of that poorly water soluble drug, and therefore the bioavailability was increased. Okay, this I can skip. Yeah, this you can see here. The drug is not soluble, and after the plasma treatment, it is soluble. So the bioavailability was increased. In another case, we have developed, this will take just 2 minutes, highly antimicrobial surfaces. What is this? Not, okay. So treating and managing wounds is a challenge, particularly in diabetic patients. What has happened? Not moving. Yeah. And the cost in managing wounds is also very high. So biofilm forming bacteria like S. aureus, S. epidermis, which are commonly found on woods. So treating them is a challenge, particularly when you have a resistance to certain antibiotics. And therefore, what we did is we created scaffolds. This work was done with BARC. They had this cryogenic bath, and we created agarose uh, and chitosan composite scaffold. And on the scaffold, with the help of plasma, this reactor, we deposited selenium film on it. And okay, I can skip this. I can go to the direct result. And this shows here the selenium is incorporated. You can see here selenium peak, and selenium is incorporated onto the film through XPS study that we confirm. And then the zone of inhibition for two kinds of bacteria that you can see. For untreated, okay, there is no zone of inhibition, but for treated film, plasma treated, you can see a big zone of inhibition. Sometimes what happens is that we create highly antimicrobial surfaces, but then those surfaces can also damage healthy human cells. So that should not happen. And therefore, we studied cell viability analysis. And here you can see that it is not, hampering healthy cells. And for that purpose, we also did confocal microscopic images. And all those green spot that you see is of live cells. And if there would have been any dead cells, it would have been in red color. So it means that whatever we have developed is suitable for human cells. Two kinds of human cells we have studied here. And, so viability is excellent, but it is antimicrobial. So uska wo kaam karta hai, but not harmful to our body cells. And we have also studied this in vivo on the rat models. And we found that as compared to the standard betadine application, okay, our this selenium based coated antimicrobial surface also does the similar work. So I can skip this.
Sir, please
Yeah,
sum
yeah,
up.
skipping.
Sir, please sum up, please.
So wound healing, contraction, and all those things we studied. This is the last slide. So here we measured. This is pathology of wound sections and hydroxyproline content. Hydroxyproline content is an indication of formation of uh, collagen. Collagen is a basic building block of our skin, and hydroxyproline content more, it means that wound healing is better. And here we found that the hydroxyproline content in case of plasma treated scaffold was comparable with the standard betadine application. And thus, pulse plasma processing is a powerful technique to control film chemistry for various biomedical applications. Thank you.
Thank you, sir, for a scintillating and knowledgeable lecture. If you want to short questions from the audience.
Yes, sir.
Hello. Thank you, sir. Very nice lecture for the plasma treatment
Thank
of
you.
the drugs delivery. So I have one query. Can you possible the plasma treatment of the neurotransmitter?
What?
The neurotransmitter, neuromolecule, biomolecules. How can stability of the conformer of the neurotransmitter,
No idea.
like that dopamine, etc.?
I do not have idea about that.
Okay. Thank you.
Yes, sir. Thank you.
Sir, I also have a small question. Yes, thank you. So, do you find any orientation effects while coating, orientation effects of thin film deposition process?
Yeah.
Because that makes the films
Yeah.
asymmetric. asymmetric.
See, the rotations that we have to optimize, and normally of that
What
rotating
is that,
reactor.
like the speed?
Yeah, speed. Yeah, we have a stepper motor, and we can
Okay, okay.
control RPM. So
Okay.
RPM has an effect on film thickness.
Yes.
Yes, it is. So we have to optimize it.
Yes.
So in the present case, it was 30 RPM. That I have not mentioned, but it is 30 RPM.
So initially, when we started my work, I did work on the hydrogen energy storage systems.
Okay.
So there we deposit these FETI, LANI5 films. And then we found this process. So we use the same thing, stepper motor and orientation to avoid this orientation. Because that then you find the films to be graded one, and they are not uniformly coated. That was the problem, and they just crack up.
Oh,
so that was I
Yeah.
was thinking.
But here, what we have done is we have varied the duty cycle. We started with continuous wave for 2-3 minutes, then 10-10 pulse, 10-20, 10-50 like that. So the graded deposition was there, and because of that, the cross linking initially we could maintain, and then the outer surface chemistry was the suitable for the application, and because of that, the drug release rate and all those things we could control.
Right.
Yeah.
Thank you.
Thank you, sir.
Would like to share a small memento. Abhi Aji. Next speaker on the session is Dr. Vivek Kumar Gupta, who is Professor of Physics, Jammu University. And I would like to invite him to deliver his lecture. He is a research specialization in X-ray crystallography and liquid crystals, in growth of diffraction quality single crystals, crystal structure determination, atomic disorder, and he has research guidance of 18 MPhil and 12 PhD students, published around 449 research papers. This tremendous one in international journals. क्या हो रहा है?
वर्क नहीं कर रहा क्यों यार है ना हो रहा है हाँ चल जाएगा ये तो आगे का होगा नहीं पॉइंट ये किससे कर हाँ ठीक है सर
Structure. So nowadays, if any chemist synthesizes the molecule or isolates a molecule, the basic requirement of any journal is he has to supplement his finding through NMR by crystal structure. So now hardly any journal is there which accept whatever you assign the structure, chemical structure to a molecule, you have to verify it by supplementing it with your crystal structure. So this is the basic requirement. When we did our PhD work, so at that time during 90s, 90% of the people involved in crystallography were physicists, hardly any chemists. Nowadays, I don't see any laboratory without a crystal structure. People are doing crystal structure solution because of the basic requirement. Otherwise, they cannot publish their work. So nowadays, the basic physics behind crystal structure solution, then refinement, then assigning a correct structure is still a challenge, because nowadays there are very fast machines. You just put your sample within 1 hour, you can get your structure. But problem comes if your structure is somewhere, after all, it is a machine. If some wrong space group is assigned, or you can say you are unable to salvage if your some atom is vibrating, maybe it's a thermal disorder, maybe it's a positional disorder, then problem comes, you are stuck of it. Nowadays you have to supplement not your chemical structure with your crystal structure, you have to give a zip file also, in which there is no A level, no, some journals say no B level error also. So your zip file will be very, very clean. So for that, there is where you need expertise in the field of X-ray crystallography. I was just evaluating some of the posters. I hardly seen any poster without XRD study. Everywhere it is written, these are the cell parameters, this is the crystal system, this is the space group. What I want, students who are taking up this field, they must know something about what is the space group, what is its symmetry, how the disorder is resolved, which is very, very important. Because sometimes very important structure which you synthesize or isolate the molecule, if it is stuck up in disorder or some wrong assigning the space group, then machine cannot help it. It is there, the help of a crystallographer is required. So I want the students who have taken up PhD as the subject, crystallography, they must know all these things. So that with this aim, I have taken this talk. The crystal structure determination of organic molecules of biological importance assumes importance in view of the fact that any structural change observed in the conformation of these molecules due to different substitutions can lead to better understanding of their biological activity. If I take some steroid molecule, we'll come to that. If at say one position or two position there is a carbonyl group, then it is no more there may be no hydrogen bond involved in it. If we replace the carbonyl group with the hydroxy group, then OH group is there. There may be number of hydrogen bonding comes. There may be chains formed because of hydrogen bonds. So activity of the molecule drastically changes. Hardly there is any difference in the chemical structure point of view. But earlier with the carbonyl group in my molecule, there is no hydrogen bond. But as soon as I have replaced the carbonyl group with the hydroxy group, so there are number of hydrogen bonds are involved. So this is the kind of study we are doing. If one molecule is active, almost similar molecule is inactive or less active, what is the reason? So mostly sometimes CH interactions, CH pi interactions, pi interactions, hydrogen bonding. So they play important roles in assigning the biological activity to the molecule. X-ray crystallography is concerned with how atoms and molecules are arranged in a crystalline solid. So what we are having in our hand, we are placing a small piece of crystal in front of radiation. Say we are taking X-rays. So my input is a piece of crystal. What I am getting output, I am getting nothing. I am getting intensity from which plane, what intensity I am getting. I have no other information. I have to extract the information from the intensity. How molecules are sitting in the unit cell. Firstly, I have to assign the unit cell. What is my unit cell? What is ABC, alpha, beta, gamma? Then what is the symmetry involved? How molecules are related? Because there are thousands and thousands of molecules in a small sugar piece. So I cannot find out or keep track of every molecule. My aim is to restrict myself to the unit cell. Then it is the repetition of the unit cell in 3 dimensions. I can generate my whole crystal. So in my first aim is to assign a correct unit cell. ABC, alpha, beta, gamma I will get. So 99% machine will give you correct space group. But there is still a chance of 1%. Sometimes if your crystal system is say orthorhombic, you are unable to solve its crystal structure. You go back to the triclinic system because this is the least symmetric crystal system. You solve your structure in the crystal In the triclinic system, then by transformation matrix, you transform again your molecule to the orthorhombic. Mostly there are many structures which are not solved in monoclinic or orthorhombic or cubic. What we do, we solve it in the triclinic system. Then again we transform back it to the original crystal system. This is where if you go on solving number of structures, you get yourself expertise because every structure will give its own problem. And you will learn in every crystal structure. It is not that I have solved 5 crystal structure, I am a crystallographer. Still we are learning at this stage also. After the intensities have been measured, the data are subjected to complex mathematical treatment. Because in my hand, I have say one plane. I am getting intensity 1000. 112 plane. I am getting 500 intensity. This is what I have in my hand. Nowadays, I am getting very powerful machine. There may be very good accuracy, but my output is remain same, plane and intensity. I have to extract whole information from this. That's why very fast computers are required because number of mathematical treatments are there. We use direct methods for small molecules, then chemical modification method, Patterson method, etc. There are number of methods involved. So a complete understanding of any biochemical system requires a description of the function of its components in terms of their physical structure. That's why it is the necessity. Although we know a compound is very, very active and similar compound is inactive. So after finding the crystal structure of both the molecules, then we do a comparison type of things. We take 10 similar structures, then we see where there is changes are coming, how the crystal structure is getting changed and it is affecting the properties of the molecule. So X-ray diffraction studies provide the most detailed knowledge concerning physical structure. So we will come to the steroid. This is the basic nucleus of a steroid. We have 3 6-member rings, then 5-member rings, then R1 and R2, mostly 90% of the steroids, they are the methyl groups, and R3 is a chain sometimes. Mostly variation we see at the point R3. So most important classes of steroids, number of classes are there in steroids. We classify sterols, Weyl acids, corticosteroids, sex hormones, saponins, bidanolides. So these are the how we classify the steroids. Those sterols are crystalline alcohols occurring in animals, plants, oils, fats freely or esters of higher fatty acids. So again, you can see R1 and R2, they are methyl groups. This is the chemical structure of the cholesterol molecule. Very, very important molecule, you can say. So this is the chain. So Weyl acids, in Weyl acids again, you can see we have slightly changed C24 compounds. Here we have different substituent comparative to what we have seen earlier. Then comes corticosteroids, cortisol and cortisone. They are the two very, very important molecules. So outer layer of cortex of adrenal gland is the source of corticosteroids derived from cholesterol by oxidation. You can see cholesterol chain is not there here. So it is gets oxidized with cleavage of a portion of alkyl substituent on the D ring. So normally in steroids we say this is A ring, B ring, C ring and D ring. 5-membered ring we call it as the D ring. So cortisol is the most abundant of the corticosteroids, but cortisone is probably the best known. Then comes sex hormones. Sex glands secrete a number of hormones that are involved in sexual development and reproduction. So female sex hormone, we also call it as estrogens. Then male sex hormones, they are androgens. Pregnancy hormones, they are known as progestin. Hardly there is small difference of the substituents only which differentiate one hormone from the other. To give an idea how small molecular difference can have large differences when affecting humans and animals. Two hormones are shown below. This is a male hormone, testosterone. Estradiol, this is a female hormone. You can see here. So difference is we have a double bond at C1, C2 position. And this carbonyl group is replaced by the hydroxy group. There is no other difference in the molecule. So this small difference in the molecule differentiate a male from female. This is, if this hormone is present, then it is a female. If this hormone is present, this is a male hormone. So a small difference in molecular structure causes the difference between male and female. Saponins is another very important class of steroids. They are high molecular weight glycosides. You can see here, we have another glucose ring here. So these are steroid saponins are derived from the spirostan or furostan skeleton. Bidanolide is very, very important class of molecules. I have reported number of crystal structure in the series bidanolide. They are C28 steroid electron characterized by a 9-carbon side chain. You can see here 6, 7, 8, 9. This is a 9-carbon atom chain. So interest arose in bidanolides when it was found that they show anti-tumor activity in a number of animal studies. A lot of work has been done in the bidanolide series. Bidania semnifera, it is very, very important medicinal plant. It is almost whole of the country, it is there, Bidania somnifera. So that's why a lot of work has been done on Bidania somnifera class of molecules. So what we have observed in steroids, I have also worked on many molecules in steroid family. So we have seen whatever interactions we get, this is the class of packing. Either it is head to tail, they join head to head, tail to tail, or there are linear chains or angular chains. Mostly packing is like this. So this is very particular thing we have observed, and whatever study we have done in a case of molecules, we have observed also the same phenomenon. This is generally reported in the literature that in steroids, characteristic pattern observed in steroid packing is the appearance of infinite chains. Number of chains are coming. So this is a OH, this is C double bond O, it is making OHO hydrogen bonds, then go on making the chain. So state chains in which adjacent links are translationally, you can see here, it is translationally and rotationally related. So it's a translation, it is a rotationally related. Here methyl groups are down, up, rotationally related. So twisted chains, these twisted chains in which adjacent links are rotationally related. So twist chains do not lie in well-defined layer. You can see, although they are making layers, but they are not well-defined layer as shown above at A and B. So I will show you one of the molecule, crystal structure of 3-beta acetoxy, 17 alpha hydroxy. At 17 position, there is hydroxy group, 16 alpha methyl allopregnant, 20 on hemihydrate. So water molecule as a solvent, what I have got is half of the water molecule. Again, it is very difficult to assign half water molecule. I am not getting H2O. When I solved this crystal structure, I got its occupancy as 0.5, not 1. So here you require the expertise. Machine will not solve this crystal structure. It will leave this part, and this will give you A level error. So this oxygen can never be resolved by any kind of machine. So what? Because I have one atom of this carbon, one atom of this oxygen. Here I am getting half oxygen and one hydrogen. Then there is another molecule sitting at this place. So this is acting as a bridge between the two molecules. Half it is making hydrogen bond to this molecule, half it is making hydrogen bond to the other molecule, adjacent molecule. So its contribution to one molecule is half. So here you require crystallography knowledge, how to solve such kind of structures. So in this case, ABC is this and beta is this. Now, from the unit cell parameters, you can see it is monoclinic system. I have deliberately chosen this as the first structure because its space group is C2. You will not find in literature any molecule with space group C21. You will find P2, P21, C2, not C21. Why? You must think why you are unable to see any structure with a space group C21. Because C2 and C21 are same. That's why we have 230 space groups. Because we have 32 point groups, 14 brevices lattices. Space group is combination of point groups and then Brevis lattice plus translation symmetry elements. Even if you don't take translation symmetry elements into consideration, 32 multiplied by 14, it is much more than 400 or so. What you have only 230 space groups. Then question comes, why not 231? Why not 229? Why 230? Because some space groups are equivalent to each other. They are not same. I will come. I have only shown this structure because I will just show why C2 and C21 we take one space group out of the two. So you can see in this case, whatever shown in the literature, chains are formed. In my case also, hydrogen bonds, they are making chains. You can see here, half water lying at the corner of the unit cell. It is contributing to the two molecules. That's why it is half. No, space groups. Just to show this, I have taken up this picture. Space group, we have 230 space groups. Whenever you teach, there is no need of telling. Just tell the students it is a combination of 14 brevices. That is simple definition. If in the interview students say it is a combination of brevis lattices plus point groups, then also we take translation symmetry elements into consideration. The expert will say, okay, student knows the basic concept. So symmetry elements that exist in a space lattice can have translation components also. So you can see skew axis we can take in place of pure rotation. If I have point group 2, its translation symmetry element is 2, 1. If I take mirror plane, then glide plane is its translation symmetry element. If I have only two-fold rotation, here, if my point group is 2, then means rotation of 180 degree. Atoms are sitting at the corners. This I have taken as one unit cell, repeating after every, say, if cell length along x-axis is A, it is repeating. It should have the same picture. So here rotation, but when I take translation symmetry elements into consideration, then this molecule after, then it comes rotation of 180 degree and translation half of the axis. So now my definition of skew axis is rotation of 180 degree. It is 180 degree. Then I have to move half along the same axis. So this molecule will come here. This molecule will come here. So I have performed the operation. Symmetry operation has been performed, but it should appear that nothing has been changed. You can see here. If you will perform the operation of skew axis, rotation of 180 degree plus translation of half of the axis, so this molecule will come here, this will go here. This is the definition of crystal. So here thousands and thousands of molecules are sitting along x-axis, thousands and thousands of along y-axis and z-axis. This is how a crystal is made. This is the diagram of one unit cell. Because we are only concerned with the unit cell. Then we will repeat that unit cell, I can generate the crystal structure. So similarly, glide plane is the translation component of mirror, reflection plus translation, half of the axis. So it's a reflected image will come down, then we have to translate half of the axis. So its position will come here, then its position will go here, a chain will go on like this. So if I will do this operation along A axis, then it is A glide. If I do it along Y axis, it is B glide. If I do it on Z axis, it is C glide. Now we have space groups P21YA, P21YC, P21YN. Hardly very small differences there. Sometimes crystal structure gets solved in P21YA, also P21YN also. Then it will not converge to 4 or 5%. It will stuck at 7 or 8% R factor. Then you have to see there is some problem with your space group. Then maybe you are taking it as the A-axis glide. It may be a diagonal glide, N glide, P21YN. In many cases it happens because you are then stuck up. Your R factor will not come down. Then you see everything is, I am doing everything fine. There is no error, but still you are stuck up. Then you have to again see your space group. Hardly any difference between A glide and N glide. So now I will take the simplest triclinic system. We have only two space groups, P1 and P11. One is non-centrosymmetric P1, then its centrosymmetric is P11. because I have to reach to C2 and C21. That's why I am showing all this. So in P1, you know there is only one molecule in the unit cell. Atoms are only sitting at the corners. This is the definition of permittive unit cell. Then one is rotation of 360. When I will apply 360, molecule will come, atom, molecule, and whatever it may be, it will come to its position. So I have only one molecule in the unit cell. Its coordinates are x, y, z. My aim is, if I have a crystal, my aim is to find out x, y, z. That's all. I have been given a crystal to study. I will collect its data, means I will get from which plane what intensity is coming. Then I have to find out the x, y, z of the molecule. Because to locate a molecule or position of the molecule means I know its coordinates x, y, z. In triclinic, I am only concerned with one molecule. Because then in second unit cell also there is one molecule. Downside unit cell also one molecule. This side unit cell also one molecule. Whatever will be the shape of this molecule will also have the same shape. This molecule will also have the same shape. So in this case, I don't have any symmetry. This diagram shows no other symmetry except 360-degree rotation in P1 bar. I failed to get any symmetry diagram here because it is only a rotation of 360 degree at the four corners. This is the simplest space group. Now I come to P1 bar. It is a centrosymmetry space group. P1 bar means inversion. What is the definition of inversion? Everyone knows. Combined operation of rotation through 180 degree, then reflection in a plane perpendicular to the rotation axis. Earlier what I did in P1, I have rotated it through 360 degree. Now P1 bar, what is? Firstly, I have rotated to 180 degree. I have rotated to 180 degree. It will be molecule plus, means above the plane of the paper. Then I have kept my mirror on the plane of the paper. Then whatever value magnitude it is above the plane of the paper, it will come in the mirror, same amount downside of the plane of the paper. So if it is above is plus, then downside it will be minus. Now you can see one molecule is this, other molecule is this. You have now two molecules. You have to find out coordinates of two atoms. Two molecules when you solve your structures. One of this molecule, other of this molecule. So what I found, you can see now, number of symmetries. If I have placed this point as my symmetry operation point, I will give here rotation of 180 degree, then a mirror plane. So this is one symmetry point. No, I say no. Here also additional symmetry generated in the center, because you have given here rotation of 180 degree and then mirror it became minus will come here, it will become plus. So additional symmetry generated. So I have shown it additional symmetry. Okay. If I take this point, I say no, I will not apply my operation at this point. I will not apply my operation at this point. I will apply my operation at this point. Because no one can stop me to choose my origin. Origin, because you have to find x, y, z. X, y, z with respect to what? With some origin. So your origin should be very correct. So now I say I will choose this my as the origin, because whatever x, y, z you have to find out, it is related to a origin. So if I take this as the origin, this plus will come here after 180 degree, then its mirror image will become minus. And this minus will come here and its mirror image will become plus. Similarly, this, you can see whether you take this point as the origin, this point as the origin, or this point as the origin. Diagram is same. Nothing is going to change. So when you solve your crystal structure, you have to define some kind of origin. So in any points, this point, this point, this point, you will get the same thing. You will not get anything new. It is only because you are concerned with one unit cell. So this point is also giving me same diagram. This point also giving same diagram. These corner points, they are same. This is the definition of crystal. All lattice points are same. So this is where your expertise lies. You have to find out what kind of symmetries are present in a space group. So this knowledge is very, very important. Now we will come to the space P2. Monoclinic system. This is I have a permittive lattice, then if there is only one, two, then we apply operations along y-axis. Normally, it's a internationally accepted. This axis we will take as y-axis, this as x-axis, then perpendicular to the plane of the paper, z-axis. Now, definition of P2 is permittive lattice atoms only at the corners. So, this plus, 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 they are atoms at the corners of the unit cell. No rotation of 180 degree. So when I will rotate my y-axis only, so this molecule will come here, this molecule will come here. Similarly, downside, because all lattice points are same. If my x, y, z coordinates are there, now my x will become minus x, because x is this side, it is minus x, y will remain y, z will become minus z. So again, I have to find out one molecule, and then I will apply this symmetry operation on that. I will generate second molecule. Then my work is over, because in monoclinic, triclinic also I have obtained x, y, z of one molecule. In this case also I will give input, because firstly in my hand it should be known that my crystal system is monoclinic and space group is P2. Then I will give in the input when I solve crystal structure x, y, z, and then minus x. It will automatically, whatever molecule it will find at x, y, z, it will automatically change coordinates of that molecule minus x, y, minus z, and second molecule will be shown in the unit cell. This is P2. Now you can see, I have taken this as the origin. Full arrow means rotation of 180 degree. Now if I have generated this additional, if I choose this as the origin, 180 degree, this O plus will come here, it will become O minus, this O minus will come here, O plus. So additional this symmetry has been generated in the middle of the two. Whether I take this as the origin or this as the origin, my diagram will remain same. This means this is the additional symmetry I have found out in P21. Sorry, in P2. Now we'll see what happens in P21. P21 is same as P2, but it is in addition to 180 degree translation of half of the axis along the y, because I have taken this standard axis as y-axis. This is internationally followed. Actually, what is P2? P21 means P2, then translation half. When I rotated, it came here, then half of the axis along y-axis. So in P2, you see diagram was this plus, then this minus, plus, minus, plus, minus. P21, this plus, this minus. So this atom will generate here. So I have again Z2. So whatever I will give in the input, that instead of x, y, z and x minus x, y minus z, now I have minus x, 1, y2 plus y minus z. Instead of showing this molecule here, it will automatically will show molecule here, because it will add in the coordinates 0.5 to the y coordinate. So this is the difference. Arrow showing reflection plus translation. So instead of taking this as the origin, if I take this as the origin, so this molecule will come here, then it will be translated to here. So this means additional 2-1 symmetry generated at this point. Here you can see this molecule was coming here, then only full arrow means only rotation. Half arrow means rotation plus translation. So that this molecule is translated to this. So this is my origin. Now you can see the difference. P2, see, they are not the same. This diagram is full arrow at the 3 points. Here I have half arrow. This means P2 and P21 are not same. They are two different space groups, and we have to treat our crystal structures differently in P2 and P21. Now I will come to C2. You can see now here is the beauty of a
Sir,
crystallographic light.
sorry to interrupt. We are running short of
I will take only 3 minutes. I will stop here after
5
showing
minutes.
this. Hardly 2-3 minutes. This is very important. I have focus is on this. So in case of C2, you can see my basic definition of C is atoms at the corner plus one atom at the center of the unit cell. I have plus one, my half of the definition of the space group C. This plus, 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 plus. This is my C phase central lattice. Now I have to give two-fold rotation to this. This O plus will become O minus, this 180 degree. Then this will go to the another unit cell. So the unit cell which is downside this, it's this atom of that unit cell will come here. So it is not that this is coming here. No. I have taken this as the origin. This is coming here and this atom is going to the unit cell which is above. If it is going to that unit cell which is above, there is one unit cell which is downside also. This atom of that unit cell is coming at this point. You can see. Similarly here. Now you can see I have additional symmetries generated. At this point, this is full arrow means 180 degree rotation. Plus will become minus. This minus will become plus. So in between at 1/4 also now you can see this plus will become minus at this point. Then translation it will generate at this point. So not only 180 degree origin I have got. I have got 180 degree origin plus translation origin at this, half arrow at this. You apply this symmetry, this plus will become minus and translated. If you apply only rotation, this plus will come to here. Now I will take C21. Your definition of C will remain same, atoms at the corners plus 1 at the center of the unit cell. Then translation of half of the axis. Here only rotation. Here I have translated to rotation plus translation. Similarly, the unit cell which is down, this atom will come here. Now you see, you will give 180 degree rotation at 1/4. This plus will become minus, this minus will become plus, this plus will become minus. Now, if I take this as the origin, this atom will come here. Then translation of half of the axis, this will become here. So, in my case, now this as the origin 2, 1, center 2, 1, and between at 1/4, I have full arrow, which is two-fold rotation. Now, you compare both the diagrams. My diagram is starting origin full arrow, then half arrow, full arrow, half arrow. In case of 2, 1, half arrow, full arrow. So, if my space group is C21, I will transform to this by adding 1, 0, you can say 0.25 to the value of its XYZ. So, I will make it C2. If you want to convert to C2 to C21, you add 0.25 to the coordinates, whatever coordinates you are getting C2. It's only the origin. In this case, I have chosen this origin. If my space group is coming C21, instead of taking this as the origin, I will take this as the origin. You see here, we have done nothing. I have only shifted my origin by 1/4 and got the same thing what I was getting this. That's why we have 230 space groups. You will never find in literature any crystal structure with space group C21 because in the program itself, crystallography program, in the space group C2, they have written, if it is coming origin at the translation point, you convert it into the rotational point. Only shifting of the origin. You compare both the diagrams. Everything is same. Every diagram is coming same. Your unit cell will not be changed. So this is the beauty. So this kind of knowledge you teach to the students. They will never forget. Very, very interesting subject. Once you have knowledge. Very nicely explained in the book Burma Srivastava, crystallography book. You ask students to follow that book. Very nicely shown why 14 brevices lattices, why 32 point groups, why 230 space groups. Once they study this, they will never forget. So questions from your side, please. Yes, sir? Yeah. Here 1/4. Sir, here it is 1/2 will generate me the same origin. So I will shift here 1/4, then full arrow is coming. So here at origin full arrow. Diagram will be the same. Because I will get the not getting new thing which I got in P2 and P21. In C2 and C21 nothing new. Only it's your choice of selecting the origin. It is up to the student what origin he chooses when solving the crystal structure. It is the, you can say no machines. In our time, we were doing all this manually. We were plotting unit cell by taking a graph paper then copying it to the transparent paper. At that time, we cannot afford plotter pens. They were very costly. So all things and journals, they accept it. I have number of papers, handmade unit cells. Yeah, it is Burma Shri Vasu, a basic book of MSc level. This all we teach to the students at MSc level. Any other question, please?
I think one more question if you have. Otherwise, we'll conclude this session. We must thank for this informative and the way he explains the things should how it is to be taught and has to be analyzed. That is the beauty of this talk, and we are very feel excited to get this information from him. The enthusiasm was great, and that was the thing, the beauty of this lecture. Thank you very much, sir. Sir, please have a small. Thank you all the participants for the patience hearing, and so we conclude this session and invite organizing secretary for further procedures for the concluding session, valedictory session.
Thank you, sir, for concluding the session. Now we are moving to the last phase of this conference, that is valedictory session. So shortly we are going to start the valedictory session. So please be here only. Thank you. Now I would like to invite Dr. Anu Sharma and Dr. Shivangi Bisa madam for conducting this session. Thank you.
Good evening, everyone present here. On the behalf of Bikaner Technical University, I extend a very good warm welcome to all of you in the valedictory ceremony. For this, I would like to invite Professor Vivek Gupta sir, Professor R.R. Deshmukh sir, Professor Ravindra Mangal sir, Professor Ajay Nagar sir, Dr. Sudhir Bharadwaj sir, Dr. Manohar Shekhawat sir, Dr. Bhuvneshwar Sutar sir to take their seats on dais. Please come up the stage, sir. Now I would like to request Dr. Mahinder Vyasji to please give a presentation on the organizing body of this conference, that is the Condensed Matter Research Society.
Respected dais, researchers, professors, and all, ladies and gentlemen, I would like to introduce our Condensed Matter Research Society, which established in year 2022 under the State Cooperative Societies of Rajasthan. First of all, I would like to our aims and targets for which this Condensed Matter Research Society established. This society established in 2022 to encourage the research in developing countries. Society is registered under the Rajasthan Societies Cooperative Act number 28 in 1958. CMRS, I will use generally abbreviation form of Condensed Matter Research Society as a CMRS. It's encouraged the scientific community people such as research scholars, faculty members and students to do the research and training in their respective fields and means all science fields. This CMRS is working for the promotion of societies for transferring science and technologies. We are very keen in appreciating and recognize the contribution of everyone of you. Condensed Matter Research Society is working for popularization and promotion of scientific research. CMRS motivates the students and young researchers to publish and present their research work in its research journals from year 2023. Basically, our two research journals running. First is known as JCM, Journal of Condensed Matter, and number second is known as CSL, Chemical Synthesis Letters. Our target is that every year CMRS provides awards to the best researchers, scientists and students for their innovative research works. CMRS has two wings for faculties. First is for faculties and second for students. Our society organizes seminar, conference, workshop, training and awareness programs to the scientific community. To cultivate and promote general science and its branches of science. To promote conservation activities of natural resources. To create public awareness camps about the importance of science and eradicate superstition. These are two journals. Number first, Journal of Condensed Matter. It started from 2023. Its 3 volume has been published. This is the front page, in which categories all topics which you can published: nanomaterials, single crystal novel materials, photonic materials, plasmonics, etc. Number second is known as chemical synthesis letters. This is also related to chemistry wing, and first is related to physics wing. CMRS already organized too many programs. Number first, International Conference on Condensed Matter and Applied Physics during 9th and 10th October 2023 at Engineering College Bikaner, hybrid and or we can say offline and as well as online mode. Number second program has been organized International Conference on Advance in Novel Materials Towards Sustainable Futures at St. Xavier College, Ranchi. And number third, National Science Day, which organized each and every year on Feb 28th on the memory of Raman Day, Science Day. It is our forthcoming events under CMRS International Conference. We will also organize on December 13 and 31st, 2024 at Anand Niketan College, Varora, Maharashtra. Don't confuse, Varora is located in Maharashtra and Baroda is located in Gujarat. So this place is Varora, Maharashtra. And second upcoming program is International Conference on Condensed Matter and Applied Physics, going to be 12th to 15 December 2025, means next year at Engineering College Bikaner. These are few glimpses of CMRS activities. This is a Science Day event which we organized every year on 28th Feb. This is a training program under the aegis of CMRS at PhD Testing Laboratory, Regional Testing Laboratory. These are students related to MSc students, and they engage in all kinds of activities related to water testing works, etc. This is our last international conference, ICC 2023. These are members of core committee. Our respected president is also situated at Dr. Ravindra Mangala on the dais. Joint Secretary Dr. Manoj Singh Shekhawat, and these are also members. For membership, you can apply directly on our website. For honorary member, there will be no fee, and for life membership, 4,000 rupees fees. And if anybody wants to become only for 1 year, so annual fees is rupees 1,000, and for students, only 500 rupees for annually. You can contact anytime to our CMRS Society, to Engineering College Bikaner, Department of Physics. These are contact numbers, and mail address is also mentioned here. Thank you very much.
Thank you very much, sir. Now, I would like to call upon Dr. Sudhir Bharadwaj, sir, to conclude the 2 days conference.
Respected dais, and thank you everyone who are presented here offline and also online. I am very delighted that from every part of the country you came here and participate in our conference RAM 2024. So this conference actually begins approximately 6 months earlier from today. So we started contacting participants at a you can say blasting wave method. We were sending so many mails, so some of the participants was not accepting that why we are getting these mails. Then we requested that if you are getting so much mail, then make us spam mails. Okay, so that is the only way which I know how to contact people, because I don't have your other contact IDs. So sorry for that here. if your mailbox is filled with RAM 2024 mails. So now we start from day one, inaugural session. So as you know that our honorable two MLAs of the Bikaner, which are our board of management members of Bikaner Technical University, were present. So they were present in this event, and I hope that other than the waiting of them, you enjoyed the inaugural session. This was some glimpse of the inaugural session. Our respected Mangal sir, which is the president of the CMRS, and the honorable MLAs of the Bikaner. The second photograph is our energetic vice chancellor sir, and I want to say that for our university and for this program, he was always ready to help at any level. So he is not present here, but I thank you him for everything, because without his motivation and without his help, I cannot move a single step. And this is also Dr. Yaduna Singh, Dean of the Academics, Bikaner Technical University, Professor Ravindra Mangal sir, and my friend and the Joint Secretary of the event, Professor Manoj Singh Shekhawat sir. I want to say that in our team, there are 3 core members. So myself, Dr. Bhuvneshwar Suthar and Dr. MS Shekhawat, actually in each and every event, we 3 are engaged from 6 months before the event. And as you seen that for the ICC 2025, we have announced already. And on the website, you can upload the paper also. So these were the invited session. Professor Nanlal Singh from Netaji Subhash University of Technology, and Professor D.K. Divedi, Department of Physics, Material Science and Material Science, MMUT, Gorakhpur. Professor Manoj Kumar Sharma, University of Lucknow. Dr. Rajesh Kumar, IIT Roorkee. And each and every invited speaker was so kind to me that by only invitation by the mail, they accept the invitation of the invited speaker, and I thank to them. I two of our invited speakers are present here, Professor Vivek Gupta ji and Professor R.R. Deshmukh ji, and Dr. Amish Sharma from DRDO Jodhpur. And these are the some glimpse of the poster session. I hope that you interacted with each other in the poster session also. And I am very excited about the online session. Our actually attendance in the online session was more than 90%. So in offline session, I think maybe some of the participants was not means put their poster, and maybe they move here and there. But in online session, more than 95% attendance is very good, I think. So it went well. And oral sessions was also there. We will announce the some first, second, third prizes for the oral session and poster session also. And I hope that everybody enjoyed the cultural program. If you enjoyed, then you can clap for them. And the main thing in the cultural program that half of the program, other than the Sufi and the 1 or 2 songs, all the event was with means managed by our students. They didn't means they took only 2 or 3 days to prepare their event. So I thank to them.
some of the students are present here also in our core team. They are working in the our volunteer team also, which was the part of the cultural program. So I thank to them, and especially this Bhavai dance done by the Miss Khattar. I forgot the name actually. Tisha Khattar. Sorry, Tisha. And this is the second day invited session. Professor Arun Basil uh, join us from the Boston, USA, and Professor Pavan Kumar Kularia from JNU, and Dr. Vinod Singh from the DTU Delhi, and Professor Anami Bhargav is with us right now. He is from Dungar College, Bikaner. Professor R.R. Deshmukh, Institute of Chemical Technology, Mumbai, and Professor Vivek Kumar Gupta. He was also in the last conference with us. So second day online parallel sessions was also going well, and today's poster session, I think this picture shows that interaction was very good with you each other. So thank you very much. Thank you again. You came here by a long travel. Some of the participants came from the Kerala and I think Northeast also. So I thank you very much.
Moving to the most excited part of this today event, the award ceremony, I would like to call Professor Arvind Sharma ji to present the Best Oral Presentation Award to Mahima Tyagi, paper ID S10005. Mahima Tyagi, if you are here, please come on stage. Thank you so much, sir. For the second best oral presentation, I would like to call Professor Anami Bhargavji to present the award to Shushmita Mohanta, paper ID C10008. Miss Shushmita Mohanta. Sushmita ma'am. Yes. Thank you so much, sir. And for the best oral presentation, at the first position is Deepak Kumar, paper ID paper ID O20013. And I would like to request Professor A.G. Nagar, sir, to please present this award. Anybody else on his behalf can take this award. Thank you so much, sir. For the best winner, for the best poster presentation awards, I would like to call Mahinder Vyasji to present the third best poster award to Miss Rekha Kumari, poster number A10045. Anybody else can take this award? On behalf of Ms. Rekha, is there anybody else who can receive this award? Okay, we will send it afterwards. Sir, आप खड़े हैं ना, तो किसी और को बुला लेते हैं. For the second position, it's Dr. Shiju E. Dr. Shiju E. from Institute of Science and Technology, Chinmay Vishwa Vidyapeeth, Kerala. Anybody else? Okay, for the first position, Shweta Kumari from Central University of Himachal Pradesh. I think we have to send their awards to their house. For the session 2, the third position is acquired by Anamika Sharma from IIT Patna, Bihar. Now I would like to request Shiv Kumar Tak sir to please present the award for the second position. Miss Kanchan Meena from SN Bose National Center for Basic Sciences, Kolkata. Are you present, ma'am? Okay, for the first position, it's Suchismita Behera. P. Suchismita Behera from IIT Madras, Chennai. Thank you so much, sir.
Now, this is the time to deliver our sincere thanks to most energetic person, Dr. Ravindra Mangal sir. For this, I would like to invite Professor Vivek Gupta sir to present a token of thanks to sir. Thank you very much, sir. Now, I would like to Professor R.R. Deshmukh sir to present sincere thanks to Dr. Ajay Nagar sir for their efforts. Thank you very much, sir. Now, I would like to call upon Dr. Bhuvnesh Ustar sir to for vote of thanks.
थैंक यू मैडम. वास्तव में सर टफ काम है. काम करना इजी है इसके कंपैरिजन में. I would like to thank all the invited speakers, advisory board members, all the participants who come from different part of the country and attend this conference offline here and present their work in oral and poster sessions and listen all the invited sessions carefully and hope enhance their knowledge. All the participants from the different part of the countries in online mode, I would like to present some database which will reflect something about the conference. We are getting about 700 registration online, about 500 abstracts. Out of them, 340 abstracts are selected and registered for online and offline mode both. The abstract come from all over the country. It is from Kashmir to Kanyakumari, Assam to Rajasthan. Most of the contributions from the Rajasthan. Apart from that, we got second position from UP, Maharashtra, Gujarat, Kerala, Telangana, Tamil Nadu, Uttarakhand, Assam, Manipur, Meghalaya, Mizoram, capital city, New Delhi, Chandigarh, Bihar, Jharkhand, Jammu Kashmir, each and every state. Few participants from out of the countries that are registered from Canada, China, Georgia, Thailand, and Saudi Arabia too. One invited speaker also from USA. He presented well their work. We are also thankful to Professor Bansal. Thank you. Thank you to all participants. Okay.
Thank you very much, sir.
If anybody from the audience wants to share his 2-day experience can come on stage. Your feedback is most invited. So that we can perform better next time. So all are satisfied. We will love to hear you, sir, please.
Okay, thank you, ma'am. It is very tough task to output up the feedback of this conference. But I would like to thanks convener sir to get me the opportunity to give the feedbacks. But really, I feel the all speakers, invited speakers, oral speakers, and participants is the very informative and some systematic knowledge for the research for the young researchers. I have really enjoyed to all lectures in the invited speakers and the questions and sessions. The food is also good, so I have really enjoyed the hospitality that is good. Uh, Actually, I was first international conference attend in 2013, and the second international conference. That is not doesn't matter how many conference I have attended, but really I have enjoyed. I have learned something new to develop the research and writing the paper skills. And second thing, the basic knowledge is most important thing to sharing the knowledge for your expertise. In the last lectures, Professor Vivek Gupta sir as giving the very basic knowledge in crystallography, and that is very difficult to understand how many fold geometry which is possible in the nature as well as in the science community. Thank you to all of you. So that is not any negative feedback in this conference. I have really enjoyed to Bikaner as well as all participants, and that is the volunteers of the conference is very helpful for pick the hotel and drop in conference venue. Thank you, sir.
Okay, thank you very much, sir. Anybody else want to say something? Any female participants? Sir, कुछ बोलना okay.
Dignitaries on the dais, dear participants, students. Today, I'm going to speak in Hindi, though I am aware that my Hindi is not good. It's Bombaya Hindi. ये कॉन्फ्रेंस के बारे में मुझे भी सर 4-5 ईमेल आए थे, but then I think in the second email itself I responded. आपको रिस्पॉन्स किया मैंने, उसके बाद भी ईमेल आते रहे. एक टाइम ऐसा लगा कि शायद मेरा एब्स्ट्रैक्ट इनको नहीं मिला होगा, बट बाद में कंफर्मेशन हो गया कि मिला है. यहाँ पे आने के बाद में बहुत अच्छा लगा. यहाँ का क्लाइमेट ये टाइम पीरियड में तो अच्छा था. फूड एक्सलेंट, मैंने बहुत एंजॉय किया फूड. यहाँ पे लोग भी बहुत बढ़िया है. थोड़ा सा डिले मॉर्निंग में हुआ, ऑफ कोर्स जब हम पॉलिटिशियंस को बुलाते हैं तो ये होता है, तो इसमें कुछ नई बात नहीं है. मैंने देखा ऑल ओवर इंडिया पार्टिसिपेंट्स यहाँ पे आए, उन्होंने अपना अपना काम अपने तरीके से प्रेजेंट किया. काफ़ी अच्छे इंटरेक्टिव सेशंस भी रहे हैं. कल्चरल प्रोग्राम सर बहुत बढ़िया था. What I felt is just, the dance made by that girl on nails and, the sword and glass pieces. I felt it little, inhuman kind of. I don't know why, but सर मुझे वो थोड़ा सा ना कि कोई ऐसे नुकीले खिले पे डांस करता है या कोई इस पे या कांच के पीस पे, तो वो मुझे थोड़ा अच्छा नहीं लगा सर. ओके, वो थोड़ा मुझे इनह्यूमन जैसा लगा. मे बी यू मे हैव अ डिफरेंट परसेप्शन देन मी, और ऑडियंस में हैव अ डिफरेंट परसेप्शन. And again, I applied my physics knowledge, and then I thought that, okay, those nails might have the top diameter of 2 to 3 millimeters, and thereby, okay, so thoda surface area uska बढ़ा दिया रहेगा. And then again, force, pressure, area, okay, looking that into the those parameters into the calculations, I feel that if those are nails are not very sharp and blunt, okay, then probably acceptable. But as far as those pieces of glass are concerned, there are chances that may get break and, may injure the dancer. So ये हो सकता है. So इसके लिए मुझे वो देखने के टाइम पे थोड़ा सा डर सा महसूस हुआ. वो ग्लास पे वो जो पैर रखती थी, कभी भी टूटने का संभव है, वो अपने हाथ में नहीं है. वो पैरामीटर टूट गया, पैर के अंदर गया, तो मुझे थोड़ा सा देखने के टाइम पे थोड़ा सर मैं अनकंफर्टेबल हुआ था. बट ये नेल्स के ऊपर का जो है, तो मैं थोड़ा माइंड में इमीडिएटली वर्कआउट कर लिया कि अपना पैर का सरफेस एरिया और ये वो सब, तो इट्स मैनेजेबल. वो मैंने कैलकुलेशन से पता कर लिया वो. बट वो जो ग्लास पीस का था ना, वो मुझे, लेकिन डांस बढ़िया बहुत था. सब परफॉर्मेंस बहुत अच्छे थे. सूफी सॉन्ग्स तो सबने एंजॉय किया. सो आई एंजॉय ऑल अरेंजमेंट एवरीथिंग. एंड जब भी मैंने कभी भारद्वाज सर या शेखावत सर से कभी भी कांटेक्ट किया रहेगा, एसएमएस किया रहेगा, जैसा मेरा बुकिंग हो गया, देन सर व्हाट इज द अरेंजमेंट, इज देयर एनी अरेंजमेंट टू पिक अप एंड देन ड्रॉप, इमीडिएटली दे रिस्पोंडेड वेरी वेल. सो आई एम वेरी मच थैंकफुल टू यू सर. एंड बाद में मुझे पता चला कि दीज आर सीजन प्लेयर्स. वो बहुत सारे कॉन्फ्रेंसेस उन्होंने ऑर्गेनाइज किए हैं, एंड देयर टीम इज एक्सलेंट. ये भी मुझे पता चला कि उनके टीम में किसी को समझो ऑनलाइन का अरेंजमेंट का दिया है, किसी को फूड का, हॉस्पिटैलिटी का, ट्रैवल का दिया है. सो दे हैव बीन डूइंग दिस for years. And अभी वो लेवल पे चले गए हैं जो उनका अभी एक्सपर्टीज माना जाएगा कि ये हॉस्पिटलिटी में एक्सपर्ट हो गए. So that expertise that these people have got and is very commendable. Thank you very much, sir.
शलभ जी. अब मैं मनोज शेखावत सर से आग्रह करना चाहती हूँ कि शलभ बंसल जी, जिन्होंने हमारे जो भी यहाँ फूड फैसिलिटी हमें प्रोवाइड की गई थी, उसका सारी जिम्मेदारी सर ने ही ली थी. सर ज्यादा
शलभ बंसल जी स्टेज पे आ जाइए. आप लोगों ने जो फूड एंजॉय किया है, उनके पीछे जो आपकी बस में जो भी प्रॉब्लम्स हुई है, मुझे कुछ कहने की ज़रूरत नहीं है. ये हैं उसके जिम्मेदार. और जो भी अकोमोडेशन वगैरह में अगर कुछ हुआ है तो उनके लिए ये जिम्मेदार हैं. तो ये हमारे टीम का 3 हम सामने दिखते हैं. मैं, भुवनेश सर और मनोज सिंह शेखावत सर, और 4th ये हैं.
Now I would like to invite all of you for the group photograph. The organizing committee members, participants. कुछ पार्टिसिपेंट्स का भी हो जाएगा सर, आ जाएंगे. There will be high tea after this group photograph.
आप सभी आइए.
Students, the organizing committee members, participants, please come on stage. Students, please come on.
सभी वॉलंटियर्स भी आ जाएं.
Student volunteers, please also come on stage. This is a most remarkable memory which we will keep with us.
बच्चे अपने आगे बैठे हैं. स्टूडेंट वॉलंटियर्स आगे बैठेंगे. टीशा. Volunteers, please come to the stage. और स्टूडेंट आप लोग आगे बैठो.